Okay. No. Yeah. Okay. I mean, actually, is this one? Is this one on? Oh yeah. This one is also on. This one. Ah, good. Yeah. Okay. Should we try to get the? That's good. And we're streaming. Cool. Okay. Welcome everybody. This is the ML workshop 2026. So a little bit different this year. So as we know, not everybody was able to travel to the US this year. So we did this thing where we have two events going concurrently. And if you just look online on the ML Family Workshop, you can see what's been going on in Paris. And so I believe some of the Paris talks will be available, hopefully recorded later. So we can find them online after the event. So some of the sessions might look a little funny, and that's just because we're co-locating, bilocating, and so there's you'll see, for example, Gaga will be giving that talk in Paris right after Matthew's keynote this morning. So if you'd like to see the full session, you can see it on the ML website here. We're going to do live Q&A. Also, folks will be asking questions online, and they have about 30 people in Paris also listening in. So. Anyway, so just wanted to say thank you to, over here we have our program committee from this year. So as usual with the workshop, it's very easy to find program committee members, and then we hope we get a lot of submissions. And so, maybe we can encourage people to submit to the workshops to keep them going. But we had lots of great people reviewing the submissions this year. And thanks also to the co-chairs, Gabrielle and Benoit, for helping organize. So with that, I'd like to introduce Matthew Flatt to give the keynote for today. So probably some of you saw Oliver's talk earlier at ICFP about PICT. And if I understand correctly, Matthew, all of his slides are going to be using PICT, which is going to be very fun to see. But he'll be telling us about the language that actually makes all of that work, Rhombus. So yeah, Matthew, come on up.
That's right. Thanks for that introduction. Let me get plugged in here. See, did it connect? There we go. All right. Well, thanks for that introduction. Thanks for being here, everyone. I'm going to tell you about the Rhombus programming language. As you may know, Rhombus is derived from Racket. It's built on Racket. The most obvious difference is that where Racket uses Lisp-style syntax, Rhombus uses more conventional style syntax. So arithmetic looks like arithmetic. Function calls look like function calls. Array and field access look like array and field access in Rhombus. Now before I go a little bit forward, let's address a question that's on some people's mind that I talk to these days. It's 2026. Really, a new programming language? After all, there are these things called AI, agentic coding agents out there, and they really like to write Python code. They're good at it, right? Do we need new languages, or should we just let them write it in the languages they know? Of course, these agents not only like Python, they like Camel as well, right? They'll write good Camel for you. And the people here probably will choose Camel over Python most of the time. Because why? Not just to look cool at the ML workshop, but because you get more guarantees, right? There's a smaller boundary between what you want to express and the code that you get out there. So it may be, it's certainly the case that these agents are just as happy to write in any other language, including some domain-specific language that's closer to your domain, makes easier communication between the human and the coding agent. And it may be that, in fact, DSLs are going to be a big part of having agents generate code that we believe and understand how it works. Right? I'm not going to say any more about it, just to suggest that this is a reason to perhaps continue pursuing systems for domain-specific languages. And that, after all, is the Racket way of thinking. So just that we're all on the same page here, we're talking about domain-specific languages, language-oriented programming, which means you have a problem to solve. What's the right language for that? And historically, we have little embedded domain-specific languages like Lex and Yak that were about bridging the gap for writing parsers, or regex when you want to do even simpler sort of parsing tasks. These things are embedded in languages in various ways. I would put nanopass in a similar category for building up other compiler passes. Domain-specific languages and embedded domain-specific languages are very big right now. If you look around, you'll find Jump in the Julia world, or Halide. Halide is its own language, but also embedded in C++. So there's a kind of continuum there even within Halide, or React plus JSX. Domain-specific languages are going to happen. We've seen this over and over again because programmers find them so valuable. I would put slideshow and pict, the languages that I'm using to write these slides in that category, or Scribble, which is the Racket documentation languages. These, to varying degrees, introduce new kinds of syntax or just new abstractions in the form of functions and classes, which is more the case with slideshow, but they're still kind of domain-specific language. And then there are extreme examples, whole new languages, like for Racket, the most famous one we have is the Uncharted series of games and The Last of Us were built with a language that was implemented on top of Racket. So a lot of the most prominent users of Racket didn't really want Racket. They wanted some other language, and they built it on top of Racket. So how do you get your own language? How do you get a domain-specific language? We all know this, right? You start with the source syntax, and you parse it into some AST, and you compile that AST down to the executable. Well, you don't have to go to machine code necessarily, as I've suggested by the ones and zeros there. Your target can be another programming language, and that's generally the sane way to do things these days. Target JavaScript or something else. Now, what if the language that you target is close to the language that you wanted in the first place, right? Then a way to smooth all of this out, a good way to write a compiler or to plug into the compiler is to have a macro system in your main language. So think of macros not just as a way of abstracting over some syntax patterns in your source language, but a way of plugging in to the compiler to get the kind of compilation you want at the end target. For the purposes of today, I'm going to call this the big Lisp and scheme idea. Right? The idea that you can build this into your language, and now you don't need an extra tool. It's just your regular run or make or compile to get your extended language to run on top of your target language, which then compiles onto machine code or something. Okay, so the next thing you might want, though, is a language that's not just an extension of your base Lisp or Scheme or ML or whatever, but some languages that's smaller, maybe, or quite different from your original language. So what we do in the Racket world is we start hashlang something, and that something determines the meaning of the rest of the thing in the file. Right? So it's a kind of macro import in that you're saying, pull in these bindings just in the same way that we could define and export macros, but it's giving us a starting point. Right? So I'll call that, for the purposes of today, that's the big Racket idea. The idea that we declare the language at the top, that we use the macro machinery to define whole new languages. Right? And not just that we can plug it in this way, but that the machinery we give you for macros, for expressing macros and making transformation, is powerful. And you can build whole new languages with it, and interesting languages where different parts of the original program need to communicate with each other in the sense of binding and use. So you can build a DSL that way. Why do we think it's a good way? Just to recap in general, it's because this way of building language extensions scales from very simple tasks, where you really do just want to avoid some repeated code, to something where you want to make a library for an embedded DSL, like slideshow, or something with more syntax, like a version of strl, say, right? Where the module system is not only letting you import things, but also sort of drawing a line between the inside, the implementation details, and the outside that users can see. Right? So modularity and so on. And then you can keep going along this path to get to the hashlang mechanism, where you get to change the surface syntax completely. Right? So you can use the same mechanisms, the same DSL for writing DSLs to work with all of these tasks. So this is why we keep pursuing a macro approach to extensible languages. Now, as I just noted, when you put hashlang here, you get control over the rest of the body of the module. So you can already in Racket change the surface syntax, and we do for things like the documentation language. So going on to Rhombus then, what is really new here? We do hashling Rhombus, and it's running in Dr. Racket and so on. But what I'm going to talk about today is all the other pieces that we built on top of this within Rhombus to improve the DSL for writing DSLs. In particular, it turns out that a lot of people have a DSL in mind that's not parenthesized prefix syntax. So just changing the native way of expressing things in Rhombus is one step along that, but I'm going to try to go into some of the other ways that we support writing DSLs today. So let me start out by showing you a few things that Rhombus can do to give you a sense of what pieces we're going to need underneath. Here I've written kind of Java style, a base expression class, and then Lambda app and var subclasses. But no one in this room or on the live stream there would like to write it that way. You want to write it more like on the right here. You want to write data type, have the three data types right there. Right? So how could we get from the thing on the right, which is what you want to write, to the thing on the left, which is what Rhombus natively supports? Right? So I've drawn the arrow to the green like where you want to go, but really the expansion needs to go the other direction. Right? So here's the implementation in Rhombus. I'm going to dwell on this just a little bit to get you warmed up to how we're thinking about things. You see, we're defining a definition macro as opposed to an expression macro. These quote marks here, single quotes are not strings. They quote code in the same sense as quote in Lisp. Right? So inside these quotes, we have to follow the same sort of base rules, which I will talk about more, as we do outside the quotes. And the indenter works and so on. So it's not just free-form, unparsed characters. You see that I've written data type here because that's what we're defining. And then $ type, just as you would expect, $ is escape within a pattern. So I'm writing some code form here, but I'm using it as a pattern. And then I have escapes in that pattern. So this is match any data type followed by whatever binds that thing as you match it to type. And then we have vertical bars for each variant. The ellipses here, the 3 dots, that's not places where I've left out code. This is Rhombus code. And those ellipses mean repeat this thing 0 or more times. So here we're saying each variant has any number of fields. And we're saying there are any number of variant clauses. Because I put the ... dots there right after a vertical bar, it means repeat the preceding vertical bars any number of times. And then we do the same thing on the expansion. So we're generating a class for that base type, expression in this case, and then we're generating a class for each variant that extends that. And we have to use the ... dots consistently here, so any number of fields for each variant, and then any number of variants like that. Okay, so that's an example, and we're going to dig into a little more of the details of how that works, but let me show you some more examples. Here is a function definition with multiple cases, the same sort of thing you would do in Camel. And you can see we've got some pattern matching on the argument here. So this is the type of, when we have a lambda, we're going to hit this case. When we have an app, we hit this case, and so on. So how would you know it's pattern matching? Well, you would have seen that lambda was defined before, just like on the previous slides. For the environment argument here, I'm using a slightly different form. I'm using the variable named gamma. Then I'm using 2 colons that you can read as sort of like a type. It's saying gamma is going to be an environment thing. Rhombus is not a statically typed language, but there is some static information. So what's going to happen is it's going to check at runtime that it really has the shape of an environment. And then when we use gamma, we're going to know that's an environment. So that'll buy us some things in terms of avoiding checks, redundant checks, and so on. But really, these annotated bindings and pattern matching bindings, how many different things can you use in this binding position? Well, any number of things. Both of these are actually just extensions in the binding space as opposed to the expression space. So one of the things Rhombus does, generalizing compared to Racket and other schemes, is have more places where you can write expansion. And this is similar to the way that patterns can be extensible in various ML-like languages, but it's just integrated into the whole thing. So all binding positions are macro extensible, and therefore all binding positions are, you can use pattern matching, pervasive pattern matching. Now you might want to write type of like that, or maybe if we can have our own binding forms, maybe I want to write the argument like this. I'm still writing a function, and this is still a binding form, although it's binding multiple things now, gamma and ID and body. how would I actually do this? Well, here is going to be one way of implementing that binding macro. So I say bind.macro as opposed to defen.macro or expr.macro. Because this symbol is the one sitting between two escapes, it means I'm binding this infix operator. And env and expr are going to be matched to the two sides of that binding operator. And in this case, I'm deciding, well, just turn that into a list pattern. So when a function says give me a turnstile thing, it actually means give me a list of two things. And then if we need to make that more opaque so that someone can't actually use list directly, we could do a little bit more. But I'm just going to use it directly like this. So that's on the binding side, but you see here I'm calling type of, and I'm using turnstile again. But this is a function call. That's not a binding position. That would be an expression position. So I'm also going to want to add an expression operator to be consistent with my binding operator. And the way I could do this in Rhombus is just like that, an expr macro that takes two pieces again and puts them together in a list. So here the binding macro expanded to add these annotations on it to imply runtime checks and static information. On the use, I don't have to have those, right? Because they will just be arbitrary expressions. But I am being careful here because I'm defining the binding and expression part to make two things that are consistent with each other. So what you see is different places where you can extend things, and then I can use the same name in different context because the context itself will disambiguate. Okay, and I should say if you have questions at any point, interrupt me. I don't know if that's practical with the live stream, but maybe you keep a lookout. Okay, here's another thing we might do. Here, I mentioned regular expression is a classic embedded domain specific language. Sometimes it's just in the form of strings, and then you have libraries that process those strings. Sometimes you get more syntax. Here, I am adding new syntax to Rhombus for regular expressions. And you can see, you can guess that exclamation mark here means not in the regex fence. And this star here is not multiplication, it's a clean E star. So I can reuse, again, these operators in different spaces. But unlike expressions or bindings or definitions, this is not a space that was predefined. This is one I want to make myself. So I can do this. I can put it in my own regular expression library, say. And to give you a taste of how you do this, we'll come back to this a little bit more later, but to give you an overview here, my librx is going to have a space in forest form in it. And space in forest form is a little bit elaborate. It has a lot of moving pieces. The key pieces first are that it binds regex to, think of it as the runtime space, the runtime support for regex. It's not quite runtime, but let's come back to that in a minute. And meta namespace here is the compile time or expand time space. And I say it's not exactly runtime because what is runtime for the regex? It's really matching time, or really it's about the space of runtime or where you're talking about writing the patterns. So regex here is going to be the bridge between what you think of as runtime or matching time and here's what I mean by that bridge. So I'm using regex.macro to make a binding in the regex space. So this star here is something I can use in a regex. Now that I've bound it this way, and it takes left and it does something. So the lines there really are pieces I'm just leaving out for now. And then meanwhile, Rx, as I used it right up here, where you're going to put an Rx form in some expression where you're going to use its match, use the match library with this regular expression. So Rx itself is a bridge. So that's an expr macro that has some pieces between curly braces. Those pieces in curly braces are supposed to be regular expression pieces, right? So it is using regex meta.parsed, which I gave a name here, to sort of go from the expression world into the regex world, drive the parsing of the regex, and then you get something that it's going to put together with a runtime pattern matching. So that's the big idea, and we're going to see another space as an example to go into it just a little bit more. So far, so good? All right, and let's look at my third and larger example. Nth, I don't know how many examples that was. Larger example for today, the foreign function interface in Rhombus that I'm pretty proud of. So I've done a lot of foreign function stuff in Racket, and we've evolved our FFI. And this is a nice chance to reset and make something even nicer for me to use. So in this example, I'm going to make We're not going to go through all this code, but just to give you an idea, I'm going to make a racket-like logo here by drawing a red wedge, and then a blue wedge on top of that, and then a white lambda on top of that. I need to make this red and blue wedge the right size for lambda. So I need to get the size of that from Cairo, which is interesting because that needs to return a record, ext, where I pull out the height from that. So we'll see, you don't have to be too familiar with Cairo. It's like everything, a kind of PostScript-based drawing model where you have a context and you draw these shapes on top, and it puts them together for you. So we're going to be using the Cairo library that I have installed here and pull the pieces out. So you just get a sense of what that looks like, and when it runs, I just see the logo. That's because at the end, I used Cairo to save it to a PNG, and then I used the Racket layer thing to pull that back into something I can display in Dr. Racket, which also turns out to be based on Cairo, but never mind. That's another binding that we don't have to know about at all. So what is it looking like there? I imported the FFI library, which gave me this class with a static method load to go find libcairo dynamically, load in that DLL. But then I use this foreign linker.cairo thing. And so what that does is make cairo.fun something that'll bind a name that pulls it out of the Cairo library at runtime. Okay, so binding a name statically, obviously, to pull in at runtime. So what that means is that foreign linker, which is provided by the FFI, it's really a macro-defining macro. It is defining Cairo to define Cairo fun, which I use to define more functions. So macro-defining macros are a pervasive feature of how we put things together in Rhombus and Racket. Another piece of how this FFI works, we don't try to parse .h files at all, because that's madness. And it's reasonable to just rewrite the pieces that you need, at least in practice. That's what I found. So here, I'm writing down Cairo create using Cairo fun to imitate what looks like this in the header file. So this is regular C header declaration Cairo create, returns a Cairo drawing context given a Cairo surface. And on the Rhombus side here, I could make it look more like C. I've chosen to make it look more like Rhombus, but with some C conventions, like using star to mean pointer of. So Cairo T star, this is after a double colon, but it's not a rhombus type-like annotation. This is a foreign type. And it's a foreign type position because Cairo fun makes it that position. We haven't defined Cairo T and Cairo surface T just yet, but the star there is not part of the name. It's the star operator in that foreign type space that makes it a pointer to that type. So just like makes it easy to connect the C code and the rhombus code. That way when you use the same convention for star. Here's where Cairo T would come from. So this says Cairo T is an opaque type, Cairo surface T is an opaque type, corresponding to this C code, where it just says Cairo T is an opaque struct of some sort. Meanwhile, Cairo status in the header files in the documentation says it's just an integer. So here I'm using foreign type to say Cairo status T is the same as int T. Another thing we do on the rhombus binding is use underscore T consistently, so it's int T instead of just int. But again, that's a choice. It could have been just int. Where we have a structure definition in the Cairo header files, we could have a rhombus, slightly rhombus style, looks a little more like a rhombus class structure definition, but the same sort of information here. You see double T's instead of doubles. So I'm just trying to give you a flavor of the kinds of things we want to express here. Finally, Cairo text extent was one of the more interesting functions we called. It takes a context, or a pointer to an opaque context. It takes a string, and it gives us a pointer to a struct that has the extent of that text. String T is predefined with the FFI library. One interesting thing is that it involves a runtime convention, coercion, because on the Cairo side, it wants a char star, which is a UTF-8 encoded thing. On the Racket side, it's going to be a string, a regular string. So we'll be able to define our own types with these runtime conversions. In principle, I'm actually not going to go into that part, but you can keep in mind that sometimes you want to add these coercions, and we want to let you define your own types that do those kinds of coercions. Meanwhile, this is, if you know Cairo, this is not actually what Cairo text extents does. It doesn't allocate a record and return it to you. Actually, well, I'll come back to that in a minute, but this is an example using it where we have a context and we pass in lambda, and then I can say dot height here because the return foreign type is a pointer to a Cairo text extents, and as we saw, that has a height field inside of it. I can say that syntactically, and the compiled version of this really is going to be take a pointer, take the static offset, get the double out of that. And then what I was trying to say before is actually Cairo text extent wants you to allocate the record first, allocate the structure and pass it in. But on the rhombus side, that's really tedious. So Cairo fun has a kind of extra little mini DSL inside of it for saying you can give a name to an argument, and then you can give its initial value, and then this is the C result type. This is what I want it to look like on the rhombus side, and I implement that rhombus side by just returning the R that I allocated to pass it. Okay, so this is the kind of things we want to be able to express, and what you see is most relevant here is that there's a notion, there's some runtime support, and there's these different macros, and then especially there's this C type space that's like regex or expression or binding that we want to be able to implement and make choices about. Like it doesn't look like any of the other things. Like it doesn't look like a regex on the inside or like a binding on the inside. Okay, so we're going to get into a little more of the rhombus mechanics in a minute. First, a question? Yes, that's right. String T involves a conversion. So it'll allocate a suitably long C char star, do a UTF-8 conversion into it, and pass it in. It's predefined, but it's not special. You could define string T yourself. So we not only want this C-type space, we want users to be able to write their own types to drop in. That's a big part of the racket historically. FFI, making it convenient, is letting you define your own types and conversions like that. Okay, yep.
So do you have a base like C-level FFI defined with maybe Cairo is just a thin wrapper on top of it, but like maybe for each different language FFI that I want, I can create one of these.
Yeah, so the question is about, do we have a base C one, and if you had different languages, you might need different bases. Right, yeah, we only have a CFFI so far. As we look more at running on a browser, we'll need a WASM JavaScript FFI as well. So I'm going to focus on the C one today. Yep. Okay, great, thanks. So we're going to do this in rhombus. Now I want to, as we start getting into, you're going to wonder, does this thing in rhombus work like this other thing in this other language? So let me talk a little bit, sort of position the rhombus and racket macro system with respect to things you may know better. Of course, you're familiar with the notion of macro as take some text and rearrange the text at the very beginning, right? That is CPP. That is LaTeX or tech, right? All of your favorite ones are in that category? No, those are your least favorite, right? So no one does this anymore. We know not to do that anymore. Most macro systems are working at the AST level here. So this would include PPX and Camel, right? You define your manipulations, your rewrites in terms of some AST, and that's what template Haskell does, and Scala and Elixir are in this category. And you notice I didn't put rhombus in this category yet. You'll see why. I'll mention lean. Lean is its own interesting case where you do work on ASTs to rearrange things, but you also get to control how the source is turned into the AST. You get to add new AST forms. So I'm a big fan of lean. They do things differently than we do, but they're sort of covering both of these ends. Often you end up defining two things that work together in that way, not unlike the way I define binding and expression to work together. But rhombus coming from racket is coming from the Lisp prediction, where there's a key difference in the picture, which is this intermediate step between the text and the AST proper. So when I say AST, I really mean I know this is a definition with a lambda with these bindings and so on. But in Lisp and racket and rhombus macros, you have this intermediate notion, some structure that's, of course, S expressions in the Lisp world that's not an AST yet. At least the way I'm using these words. S expressions is not what I would call the AST. The AST is what I'm going to expand those S expressions to that the rest of my compiler pipeline deals with. And other languages with macros have this concept of token trees. Is that what it's called in Rust? I think maybe so. Or maybe I'm taking that from Dylan, I forget now. In Rhombus, one of the new things in Rhombus is a new thing in this category. A new token tree thing that's replacing S expressions for Rhombus's purpose, but sharing the same goal of S expressions, of having this intermediate, semi-structured data that's on the way to an AST, but not an AST yet. And the advantage here is that a macro doesn't have to masquerade as a function call or something else. It can have its own syntax that will be split up into different pieces. So is this how Lisp macros work? A loop like that? Well, I mean, that's what we sort of think of. We think of it expanding S expressions to S expressions. But really, it's more like this, because what has to happen is it does some expansion, macro expansion maybe, and it gets to a lambda, and it sees that there's a binding name. That name can shadow some other macros. So as you go on the inside, you're not triggering macros that correspond to the argument name. So you have to think of Lisp and things like Lisp as a cycle evolving an S expression into an AST, but there's an interplay here between those two parts. And Scheme and Racket and Rhombus are going to be very much in that style. Rust is also. So Rust with its token trees, there's a similar sort of interplay. The difference where I drop out Lisp is that with Scheme and what came after, we have a notion of scope that's built into our S expression representation. So we call these syntax objects usually instead of S expressions. It means that our identifiers in particular have not only the name X, but also X in a particular context, particular lexical context. So that if you get X from different places, they won't be mixed up as being the same kind of X. That's a really interesting thing that I'm not going to talk about at all today. So I'm going to gloss over it. We're just going to agree there is some lexical information on those identifiers. And then where Racket sort of starts extending on what Scheme gave us is that you can have more control over the expansion parts. Your macros start to be powerful enough to make requests of the macro expander to force expansion of sub-expressions, and then maybe look at those sub-expressions and decide what to do, or communicate between different parts of the program through binding. And then where Rhombus starts elaborating on Racket is this notion of separate spaces and sublanguages. Right? The idea that there's expression space and the binding space and regular expression space and foreign type space and so on. And what that means in the abstract syntax layer is you get to define new abstract syntaxes, kind of like in Lean, just at a different point in the pipeline. Because when we introduce a new space, like regex per type, we get to control what it means to be the core of those sublanguages, as opposed to the core of expressions or something. So that really brings us to Rhombus specifically compared to the other things. Also, these ASTs, you don't have to expose them. So when you force sub-expansion, say, there's a real question of whether you should allow that to be inspected or not. Whether you should expose your core AST, because I think PPX users know if you expose the core AST, then what happens when the AST changes, right? So you might want to make choices here about what information you expose and how you expose that about the AST, and that comes out of this strategy as well. So I'm going to go into some details on basically these four parts of the pictures. I'll tell you a little more about subree notation now, the inforestation part that gets us from that into abstract syntax. I'll talk about some static information because I think that's of interest to this audience, and then also come back around to our FFI example to talk more about sublanguages and spaces. So shrubbery notation is our replacement for S expressions. You all know S expressions. Here's an S expression. Here's what it looks like if you draw that as a tree. The genius of S expressions is that the grammar is tiny. Right? There's two cases. There's atom, and then there's parenthesized thing. Totally a lie in a real implementation, right? There's all sorts of extra complications hiding behind atom there. But the high-level idea, it's really just this. And that's beautiful, but in terms of having control over the language, this minimalism cuts both ways. It means that you only get this much. And there have been many, people focus on the parentheses. There have been many proposals to replace the parentheses with something else, indentation, curly braces, what have you. But they're all meant to be rewrites into S expression. And this is the thing that Rhombus picked differently. We said it's not really the parentheses, it's the minimalism of your core representation. So let's pick something bigger that gives us more syntactic variety. It lets us get closer to some conventional notations, but still being much smaller than a real language's AST. So the shrubbery grammar is on the order of this size. Right? Again, a little bit is hiding behind Atom here, but otherwise, this is the kind of structure. Instead of one case, we have 4 kinds of parentheses that we distinguish. And then beyond that, we also have a notion of blocking and alternatives that is built right into the language. So here is a shrubbery form. And here's how it would be drawn as an AST. You can see I've got these things called groups. Roughly speaking, a group corresponds to a line. So when you make a new line, then you have a new group. And here inside the parentheses, we also have multiple groups separated by a comma instead of new lines. So same concept of group, but a little bit more syntactic variety in that you can use parentheses or new lines. And it happens that in parentheses, you need to use a comma to separate things. But you'll also notice that shrubbery notation doesn't make all the distinctions that S expressions do. So at least the way S expressions are conventionally used, anything that you want to think of as a sub-piece of this tree that can be processed independently would be broken out that way with parentheses. Whereas in Rhombus, we're going to leave a certain amount to infix parsing or precedence-based parsing. And that sort of choice is another thing, exactly how to balance that's new in Rhombus. Yes, question. Yes, that's right. When you're in some sequence of groups here, they all have consistent indentation. Yeah. So like I said, roughly elements on one line are a group. So that's one group. This is 2 groups. Also, semicolon can be used like a new line. So this is also 2 groups. And then it's this colon that starts a new block. If you remember the grammar, you probably don't. But a block is a sequence of groups. So these groups with new lines are at the same indentation. And then we also have vertical bars. It's not obvious to have both colons and vertical bars. But if and other kinds of control flow and other kinds of choices are so common that we found it useful to build that layer of syntax in as well at the same level as parentheses and groups and so on. So vertical bars, they don't have to be on a new line. If you do, then all the vertical bars are lined up together. Even if they're on the same line, they start new sequences of groups on the inside. Unlike some other languages that use indentation-based syntax, even inside of a parentheses, all the rules stay the same. Right? The only difference is that groups are separated by commas at the top level. But of course, we have nested groups here that have their own nested rules. So here, this is 2 groups, x and minus y, whether they're on one line or 2. Quotes are more similar to parentheses than anything. Inside of quotes, again, the indentation rules still apply. But quotes continue to use new line to separate groups instead of comma. So it's really just that. When I write it this way, often I will write it this way instead. Inside the quotes or parentheses or so on, it doesn't matter the indentation relative to the quotes or commas. But once you pick something inside, then you stay consistent inside. Okay? And the indenter suggests certain relationships between the quote or parentheses. Okay, so those rules have worked out, and they're unfortunately more complicated than I made them seem here. As a user, they feel relatively straightforward. I think what's most important is not the choice of white space syntax or those particular rules, but just picking a grammar on this scale. All right, so once we have that, as we said, this shrubbery notation is leaving some parsing for later. What does that mean? Like, this is all one group, right? It's a group that's a mixture of identifiers and operators and numbers. Right? So we call the process of taking this relatively flat sequence of things and turning it into a tree inforestation. So inforestation's job is to recognize that times has higher precedence than plus and give us this tree. What if we use our turnstile here? Forestation's job is going to be to somehow know that turnstile has this precedence related to plus and less than. Don't try to figure out what number it is in between those two things, because that's not going to be how it works. Let me show you how it works. This is our definition that we had before of turnstile expression. It's just taking A and B and putting them together in a list. So if I write at the prompt here, 1 turnstile 2, I'll get back the list 1, 2. Okay, what happens if I write 1 turnstile 2 plus 3? Right, is that a list plus 3, or is that a list containing 1 and 2 plus 3? And the answer is neither. It's an error. Nobody said how plus and turnstile are supposed to be related. So instead of making up something or saying that turnstile looks like this and therefore it has this kind of precedence, Rhombus says, and in forestation, as we've defined it, says you have to tell me. So one way I could tell him is say turnstile should be weaker than arithmetic. In general, after weaker than, I can name specific operators, or I can name sort of classes like arithmetic that those operators have opted into. So plus says I'm arithmetic, and times says I'm arithmetic. So I'm declaring specifically a relationship between turnstile and operators like plus and times and anything that's opted into arithmetic. So now when I say 1 turnstile 2 plus 3, I do get the list 1, 5. Right? Not 1, 2 plus 3, but of course that gets evaluated to 1 and 5. So what this is showing you is that the macro is configuring both the expansion process and providing information for forestation. Right? And these things go together because macro expansion and the parsing of forestation are tied together. And then the precedence here, it's not just that I declared it. Precedence in general is pairwise. It's not a total order. It's not even an order. You get to say which things make sense relative to together and how they make sense. Question? Yeah, so the question is, can you add precedence information later after the fact, like you import an operator? The way you would have to do that is define a new macro that expands to the old one. Yeah. But you can sort of add it on one side if it's not on the other side. So that's often good enough. Yeah. Under the hood here, if you're a parsing fan, what's going on is this is a Pratt-style precedence parser where the actions, or what Pratt called the denotations associated with each of these operators, is macro expansion. So the pieces get passed in and the macro expander takes over. You produce some result and that gets reparsed and so on. Right. I'll say that defining a macro may seem like the long way to go around if you just wanted to introduce a new operator. You didn't want to think about compile time and runtime. You just wanted to define an operator like you define a function. Yes, you can do that. That's what the operator form does. But the operator form is really a macro that expands to a function definition and then the macro that expands to call that function. Right? So that's a natural way that the pieces fit together. The big picture is that forestation and macro expansion need to work together, and when you do that, everything works as it should, including if I define this operator in some nested scope. Right? The scope and local macros are going to do the right thing in that case. Static information in Rhombus refers to this idea that I can say PS is a list of posin, so that when I do .x at the end here, I really am getting an x out of a posin, not just any old x like in Python. And how does that work? Yeah, also that PS0 there is really using the list indexing and not just any kind of looking for 0 in an object. How does that work? It's because list of posin is in we call this an annotation position. When I say annotation, you might want to think type-like. Posin and list of posin exists there, so it builds up as a type-like annotation. Here's what you know if you got a value with this information. And then colon is a binding operator that takes an annotation and propagates its information to, in this case, the binding PS. So now PS knows that it's a list of posin in a sense. It has the static information that implies that. So that when we use PS later in a macro, this is going to be the square bracket macro, right? It can find out, oh, this has static information being a list of. So it knows that's a list. So that the 0 there is a list indexing. And then, oh, also actually it's a list of posin. So it says when you get something out with the index, it's going to be a posin. So .x there really is a posin x, right? So that we can use the posin x selector directly in the compiled form there. So there's a kind of, it's a little bit like bidirectional type systems, and there's some downward flow of information and some upward flow of information. What distinguishes it and makes it less powerful in general is that, at least at the expression level, there's limited propagation from the right-hand side of a binding over to the left-hand side. Right? And this has to do with order of expansion and recursive bindings and so on. We have to place some constraints here. If you're doing your own thing with enforestation in a different space, you can make some different choices, get similar things. And so for that reason, it's not exactly a type system also. You don't get a soundness guarantee by adding in double colons in your language, in your program. But it's some piping, some infrastructure you can use to build a type system. And very quickly, this is a lot of code, but you see the way the PS0 is going to work here is that it's going to trigger the #% index macro. #% is a convention that means, I'm sorry, you have to see this name. Usually it's implicit. So just when you use square brackets, then it's implicitly using #% index. You know, and we got PS and 0 here. By default, it does a generic get. So just indexing calls the generic get function, which doesn't know it has lists to work with and has to figure it out at runtime. But if you use this part of the API that lets you find static information, then we can find out from PS that it has list information, and so it can compile as a list get instead. And then similarly, if PS says that index results have the static info posin, then we can wrap that around the outside. Okay, so that's just gives you a sense of what it's like to work on the inside with the static information piping to overall get the effects that we want. Since this has posin information, then the .x will do what we want at the end. And then, as expected, it's tight to squeeze in this large example, but I'll just do a little bit about it. You can ask me more questions about what you care about. You saw this libload and foreign function. I mentioned that foreign function is a macro. It expands to foreign def. Like just take any sort of value and give it this type. This arrow now is in the C type space, right? Meaning the type for a C function. And that really is expanding to use just a regular old find method on a foreign library object to find this export from that dynamic library. And then we get the actual Kairos status to string by taking that pointer and casting it to this C type. Right? But again, that's our foreign type sublanguage. So cast is just in the expression world, and it's bridging to the foreign type to generate the right things. At this point, you're probably wondering, like, this has got to fit into the real compiler pipeline somehow. So what are the basics? The basics are things like this. Like, here's a C representation. Make me a setter, make me a getter, make me a way to call a C function using these arguments and that result. Or here's a way that I can take a rhombus function and turn it into something that a C function can call with this representation. So it's all just about the representations that we use in the ABI, and that's a static thing that is not extensible. It's a little bigger than this, of course, because we have to deal with int 16 and 32 and so on, but just a handful of static things. This is not convenient to use directly, but we make our own type layer here where we can expand int t to the int representation, or Cairo t star to just a pointer with a particular tag on it. And we get to, as the implementation of the type space, we get to pick that. Pack and unpack are the lowest level things that'll make these opaque syntax objects that have ASTs inside of them. And then we get to define what it means for type macros to pack a type or pack a pointer type and so on. So we have this intermediary between the actual AST underneath, hidden under pack and unpack, and what we give publicly for other macros to implement. For the actual implementation, you encode it in S expression, so I might have a representation in a category and something about static information in there. And then I make the public pack type use the private pack on something of that shape. Int, for example, is just packing the int representation with the same static information as rhombus is int. That's what that means. Whereas an opaque type would say opaque, and like if it says opaque, like when we did a foreign type of Cairo-T, we just made an opaque type with the tag Cairo-T. And then you can kind of get the idea how it goes from there. When you're unpacking a representation, usually you can't use opaque types, so your unpack that knows about the AST internal structures can give a good error message and hide away the other details of the internal representation and so on. Like star would have the type star macro needs to expand some other type, look at its representation and annotations, and make suitable derivatives of that. Right? Say the C representation is a pointer with some tag, so we can do a little sanity checking. And the static information is a pointer to whatever the static information of that type is. Right? Glossing over lots of the details, but I think you get the idea here. When you do new of a type, we parse that, and then we use some malloc core runtime function on this foreign inline size of to get the size of that representation. And so on. That's like structs need to do parsing of the field type. So the big picture overall here was to make this type, we instantiated the space using space and forest. We get to pick the AST representation, which we can keep private or public as much as we want. We get to define the initial bindings of that space, int, t, star, and so on, using macros, the same sort of technique that we use for expressions and bindings. And then if we want others to be able to define new foreign types, as we do, because they might want to plug in their own conversions and so on, then you can expose type.macro for use externally as well. So you get to use all of the same mechanisms that we used for expressions for this new thing, and that's how the domain-specific language fits together and makes these different dimensions easier to write. So I sort of blasted you with 4 little pieces of the pipeline here. If I had more time to explain more stuff, then I could make this a lot simpler. We would get down and see that the really important part in here was this notion of token trees with syntax objects with some binding information on them. So if you're interested in that, I will give you the phrase set of scopes, and you can go look in that direction. So that's the keywords there. Combining that piece with this per space and forestation, the parsing mixed with expansion with the idea of these ASTs and the mediation through the inforestation engine that you instantiate for each of these different spaces. When you have both of those pieces together, then static information was something that came out of that was built on top of that. Expressions and bindings and binding patterns were all built in that. So there you go. That's an introduction to the internals of rhombus. Thanks.
Ooh, okay, cool. We have questions for Matthew. We can pass this thing around. And also online, we can, if anybody, I can monitor online.
Does Matthew have a microphone? Okay, lovely talk. Yeah, I have a lot of questions. I'll just do them after other people. The one I'm most curious about, though, is if you could talk a little bit more about the type annotations and this not being a type system, because I think from the examples on the slide, it's like you could reasonably get away with calling this a dynamic type system. You mentioned stuff about plumbing around like type information. Is it like macros have to do stuff with the types themselves, or?
Yeah, macros have to do things with the static information itself, the type-like thing. So it's not a type system. Here's one reason why. If I said .z here, do I get an error? There is no z. In rhombus, it turns out you can use rhombus/static where you would get an error for that. But then if you keep pushing on it, if you add an intermediate variable, then you can end up hiding. It can lose track of the information. It doesn't propagate it as strongly as you would expect in a normal inferencing type system. So even static lets do certain things. And the way I put it at the end of the day, just because you wrote colon and it didn't get any errors and you said static, even if you may still get errors at runtime that are of the sort that a type system usually rules out. So I don't know if that's answering your question yet. You don't look convinced yet. It's kind of the same machinery that you would need for type systems, but without the guarantees. So is it a type system?
I guess maybe my question is more, how does, because I assume that if you type ps.x, you're going to get an error here because that's not like something super well defined on a list.
Yeah, in static mode, yeah.
Okay.
Often it's when you do high order things, you have a function that accepts a PS and you misapply it, then you don't get an error. That's an example of where it loses information.
What, I guess, implements that being an error in static mode? Like what part of the code?
Yeah, it is the choice of dot. The dot operator says, am I in static mode? Well, I don't know what Z is, or I don't know what X is on a list, so I will complain. So the choice is distributed to the different syntactic forms, the different operators, or different macros, and so they get to make that choice.
Okay, cool. Thank you.
Which has its benefits and its drawbacks, of course.
Just double check this one works. So we have a question online. They said they would like to teach using the HTDP approach with algebraic data types and pattern matching with exhaustiveness as well, exhaustiveness checking, but not necessarily static types. And they were curious if Rhombus can do this. I
think the exhaustiveness check is a piece we're missing at the moment. I think it can be added. We just have not yet. It's some extra static information. Because static information doesn't have to be just types, it can be other things. So we can fit the exhaustiveness in there. If you did want a typed language, I do that sort of thing with a language called Split, which is built on top of Rhombus, et cetera, which does, it's ML in Rhombus syntax.
Quick follow-up to that. What's the status of the teaching languages for Rhombus?
Yeah. I will refer you to Sam, I think. So he and his crew have been looking at that. And where they are exactly, I think it's in progress.
Hi, thank you so much for the talk. I think in Rhombus, the syntax is very generic, but not totally generic, right? You have some biases in there in terms of like the bars for the pattern matching and things like that. And I use a lot of Lean, and they have their own biases towards wacky notations for mathematicians and things like that. Do you have a sense for whether this is just like a necessary thing where you have to at some point pick kind of what the syntax is going to feel like, or do you think there are ways to kind of push this even more generic?
You can push it even more generic. I would flip it around and say there's advantages to being opinionated. So there's a certain baseline ability for anyone to read Rhombus code, say. As long as it says #lang Rhombus instead of # something else that's picking a parser. So cuts both ways. I tend to think of it as an advantage.
Cool, thank you.
When we build DSLs, we also want to like make sometimes auto formatters. So is there any facility to go back to the printing source?
Yes. So sort of connected to the previous question, the tools can be shrubbery generic usually, right? Your auto indenter and choices about how to lay things out in general. More so even than in Scheme, because in Scheme, we say there's S expressions and you can auto-format, but really there's special roles for define and con to choose how much. And so I wanted to get away from that. But I think another part of what you were getting at is, do syntax objects carry along source information that lets you like reconstruct the exact text? Like it turns out I need that all the time for these slides. I will pick how I want it to look, and I want it to render that way on the slide. So yeah, we have worried about carrying along the concrete original literal text. You could, in principle, do things with that. Usually not the intent, but sometimes going a little beyond the intent is okay, like we do for slides. That answer what you were looking for? Okay, thanks.
Okay, I think we had time maybe for one more question.
So it's been a number of years since syntax rules and syntax case and syntax parse. And there have been other languages that have looked at this and kind of been like, this is a principled way to build a macro system. We're going to do our own thing. Our own thing in like a good way. Does Rhombus have any particular inspirations for its macro system?
It's very much syntax parse, but the big departure is declaring when you're escaping to a variable, to a variable binding, a pattern binding, as opposed to in syntax rules, unless you go out of your way to say it's literal, then it stands for anything, right? So the advantage of this explicit putting a $sign to say here's a place that can be anything, batch it to this name, is it's consistent with pattern matching generally. So we don't actually have a separate syntax parse-like form. It's all just match. Use match on list, you use it for syntax. And that has worked out well. And sort of making things more consistent relative to regular pattern matching versus syntax pattern matching has also helped. Does that answer what you were looking for?
Yes, thank you.
Yeah. But the ellipsis stuff is all from syntax case, syntax parse, syntax rules in the predecessors. Good. Tutorial at 2 o'clock. Yeah, if you want to learn more about those details, we'll give you a hands-on tutorial this afternoon.
Actually, one more question online. It says, is there enough buy-in from the Racket community for the new syntax, or are people sticking to S expressions for now? And I guess a follow-up question is like, is Racket education using the new syntax?
So like that goes back to the Jason's question before. We don't have our Rhombus HTTP teaching languages yet, so that's still with parentheses. As far as the Racket community broadly, we don't think everyone has to switch over to this. And what's true so far is it's kind of half and half. Some people are interested and want to use this, and some people really don't, and that's all fine. So Racket was always supposed to accommodate many languages, and that's where we are. Yeah.
Good. So can we thank Matthew again for the excellent keynote? Okay, so if people are interested, so the Paris session is going on, and there's an online link for the Paris session that if people are interested in viewing the Paris talks, there is one starting now, I believe. So unfortunately, we're not able to stream it here, but there is at least an online link. You can find it on the Paris website, the FPW website. The next session will be after the break, and I guess we can, of course, hang out and chat with Matthew for more questions. But yeah, thank you all. And we'll see you at the next session after the break. Great. Okay, welcome back, everyone. So next up, we have Pablo to tell us about testing incomplete programs in OCaml. This is the first of 2 talks this session, so right afterwards we'll have Byron come up. But right now, let's let Pablo take it away. Thank you.
Hi, everybody. Thank you for the introduction. So I'm Pablo Venario from University of Chile. I'm very happy to be here. This is work from my undergraduate thesis under Professor Eric Tanter. So, as the title says, is testing incomplete programs in OCaml, and it can be applied in general to other programming languages. So, let's start a little bit. I also presented this at the SRC, so I don't know if maybe you already saw this, but as you can see, we all have programs step by step, so even programming languages have idioms for this, like Rust has the to-do macro, Scala has the 3 things, Python has not implemented, and in OCaml, you can just raise an exception saying to-do. I mean, I guess everyone here has lived parts of their code and implemented. So what usually is happening when one is programming is one starts from the unimplemented, like everything is a whole, then you complete a little bit and then a little bit more. And we're also expected to test throughout the whole development cycle. So what's happening, what says at the bottom there, it's the completion refinement relation that is introduced in a recent paper at UPSLA called Incremental Certified Programming, which is a relationship between programs and that have holes. So the complete whole is at the top of the relation. So, like I was saying, we are always expected to test our code. So, say in this case for the substitution property, we have 4 unit tests and 1 property where the property is just the law of substitution. We don't want to capture variables. So, what happens if we test this program? Well, it just crashes at the 4th test, and the shrinker even tries to minimize the error. In this case, it's just an exception, so it doesn't really make a lot of sense to shrink an exception. And in the property-based case, it's a little bit... So first, what we do when we have this is we tend to skip the cases that we know are failing because we have an incomplete part, right? So what that does is that we have a disconnection between our code and test. So if we have thousands of tests and we have a very big code base and we go disconnecting tests because we're implementing a new feature and we complete this feature, we would have to reconnect this test by hand. So that's pretty error prone. So the idea is pretty simple. We would like to have a verdict of its own. It will be called incomplete. It sounds kind of obvious. That has to be different than pass and failure. But in the case as you saw before, you could say that property-based, when we reach an exception that was just trying to represent an incompleted part, we're confusing incompleteness with an error. So we would also like this to be informative. So we could add like messages where we have holes, and at the end, when we property-based test everything, we could have a nice summary. And we would keep this connection between code and tests. So I'll start with a little demo of what happens when we try to test this at the beginning, because this applies to unit testing and property-based testing, seeing property-based testing like as a more general case of unit testing. So yeah, we'll see what happens with alcotest and then how the output will look with incremental alcotest. So this is the substitution function as you already saw, and if we try to run it, we would just get this output. Oh, sorry. We would just get this output, which is totally expected, right? We have a hole where the fourth case was trying to check, right? And if we do the adaptation to Alcatraz to support like this new verdict, the output would be a little more like helpful, so to say. It would look just like that, which is, it has a lot of less noise, so to say, right? So, continuing with the presentation. Well, now, with the property-based test, this is a little bit, we'll do the same, basically. So, what I'm trying to do to show here is that we're simulating, like, we started the implementation from 0, right? So the substitution function is basically a whole, and when we do the test, we get everything incomplete, right? So that would be like the first step of the incremental development. Then if we, and this is how it would look when trying to test the property on just the completely unimplemented function. We would just get incomplete all the way, and it would signal us where we're hitting the incompleteness. In this case, we're having us 760 times, and we actually have 440 passes because it's a vacuous truth when the x doesn't belong to the free variables. So now let's say we start completing this substitution function. The output would start to look a little bit like this, so we have even more passes, and I'm going to show you immediately how this would be the current state of the substitution function in which we just applied the property-based test, right? So it's more helpful. We don't get like a whole screen of errors, red errors. We get messages where we're hitting the incompleteness. So it's pretty useful. So now say we actually want to keep working on this substitution function, and I want to and I made a mistake. I'm gonna Oh, you don't see this? No. So we would like to complete this part of the function, and we're going to introduce an error on purpose to see, to simulate a little bit what a real development would look like. We always make mistakes, right? So I'm just going to do the unnested. And say we don't know how to implement this case, so we just leave it, we just put a message on it saying and the other case we say we know how to do it, so I don't know where am I getting the syntax error? Is it? Oh. Oh, yeah. And here it would be like. Oh yeah, there we go. A little nervous. So, if we now run it with this new approach, with this new completion, we would expect to see some actually good outputs, some incompleteness, and an error. So, we actually get what we expected. We got 51 passes. We got a real failure, which we actually shrink, and we get signal where we're hitting the incompleteness. So that's like the whole point, to be able to have like an incremental development where we have help from the property-based testing framework. Now if we keep completing this, like this is the complete function, and we're still getting some errors. So yeah, now we're pretty closer to the output. We have, this would be the function. We already have a missing case, which we're supposing we don't know how to implement, but we have correctly implemented the part where we have to do this. So when we complete this, we would expect to see and now we have it completed, and now we have it all green, all passing. So that's how I would expect to work with an incremental property-based framework. So yeah. So the important thing of this, the most like important property, is that if you are already failing and you complete code that have holes, no matter how much you complete, you are still getting errors. It's similar to Gradle typing, where you have like an unknown type and you have a type error. No matter how much you complete the other type, you're still gonna be getting the type error. So the thing is, if you have a complete passing test suite and you take holes from it, what we would expect to see is just greens and yellows, right? So what is this completion refinement I talked about at the beginning? It's just, the thing is, this work is inspired by the incremental certified programming. So the problem there is that when you try to prove something in incremental certified programming and you have your code incomplete, like the property just doesn't hold, so you have to do a reformulation of the property. So that's actually very complex. So they introduced this framework and this relation of completion refinement, and they introduced this notion of reformulating the properties so they can become incremental and actually tolerate this incompleteness while you're working. So this is an example of where we have a very simple predicate that receives a term and it checks if it's equal to 0, and like what happens when we just pass it a hole, it just fails, and when we have it reformulated, it holds. Like this is just how the output would start looking, and they introduced this reformulation using a mu, and I don't know the translation of this. That way you can transform very general properties into incremental properties. But the thing is, in property-based testing, we don't have very much complicated properties. What we have is basically we're generating a random X, we're passing it through a filter, and then we're checking if it's true. So that would be like what a property-based testing framework is doing. So here, filter and check are user-provided, and they could have holes in them. Okay, so what we have to do is just applying the reformulation to this, and it's pretty simple. As you can see, you just have to replace the quality sign by the completion refinement, and this decide procedure is basically a decision procedure for mu of p, and what you can prove in COG is because in ROG, decide actually has like 3 different outputs. It can output a pass, it can output an incomplete, it can output a discarded, and it can output a fail. So what this is saying, if we decide doesn't fail on X, it also doesn't fail on the reformulated property, and this can actually guide you to implement this reformulation at the framework level in property-based testing. So where does the reformulation live, as I was saying? So the thing is, we don't have to reformulate the properties that the programmer writes. This just lives at the framework level. We just do this. We just catch the incompleteness at the runner. So we don't have like this complexity of having to reformulate everything to be tolerant to incompleteness. And it's actually not a pretty difficult change to apply. In QCheck or Camel, there's actually like a function very similar to decide, where you can just add this branch and you would be getting this support for incompleteness. So I actually evaluated this using the multi-core test. So the multi-core test is, as the name is saying, multi-core test for the OCaml compiler. So that's a very big test suite already passing. And what I did and what I expected is that if I make holes in the compiler, I should still be able to run the whole test property and having a mixture of green and yellows again, and I could have information of where this incompleteness happened in the compiler. So the point is, as this multi-core test is a pretty big suite, and the OCaml compiler is also a pretty big code base, it's actually nice to evaluate it here. So I put holes in the array functions, and so basically what's happening in the multi-core test is, like, this is the chain of calls, and an important thing is that if you raise an exception and you catch it inside the STM machinery, which is part of the multi-core test, and you don't pass it back, you could just hide it and you wouldn't be able to catch the incompleteness later. But if you actually, which is what they do, just repropagate all the exceptions, you have no problem and you can actually catch it and be having the incompleteness determined. So here I add, like, there's always some scheduling non-determinism. In some seeds, some negative test passes. In some others, you just get an incomplete. So, but that's expected from multi-threading. So these are the results. Like in the incremental QCheck runner, we get an exit code of 0, which is good. And the stock QCheck, we get an error pretty fast. We also get counted from the incompleteness cases, and we get info from the implemented parts because we're actually running the code through that implemented parts. So this is basically saying that in some tests, I remember when I was programming this, because the test was negative, and in the runner, I was adding the hole, I got a red. And basically that means my whole work was bad, because if I have a red and I make a hole, basically I'm introducing a bug by introducing incompleteness, which is not the case. But because I knew, like, this decision procedure has to worry about the cases, I knew that I had made something wrong, and the only thing I had left to do was just making correctly implementing the negation of test make, and that fixed it pretty fast. So this is what the output looks like, and this is when it says that it did not found a counterexample, and we have just a massive amount of incompleteness cases. Sometimes with other seeds, it did find a counterexample. So some related work, as you might already know, Agda has interactive holes. Hazel also has a static and dynamic semantics for holes. Here the important thing is that we need to be able to catch this signal of incompleteness, otherwise we wouldn't be able to do anything with it. And other things that are maybe similar is that in Python and in very much frameworks, as I said, you could skip or you could expect a failure, but that would still be mixing incompleteness with errors, and you would still have to reconnect once you go completing your code, which is not the best. So I would really like to get feedback if you would actually see benefit from using this third verdict. And yeah, I mean, it's a pretty simple implementation to do. It shouldn't introduce like bugs or stuff, as you could see when introducing incompleteness to the compiler, for example. And it's just good to work with like a real incremental development and having feedback all the way through. So yeah, that's it. Thank you.
Some questions for Pablo?
Hi, nice talk, thank you. I have two quick questions. The first is, why is the exit code 0 when you have incomplete things? You could imagine you're vibe coding something and the agent just sticks some incompletes in there, and then it thinks that the code is good because it saw exit code 0.
The thing is, I was actually talking about this with another professor, and I think this could actually help agents, not like reward hacking when you have like an incremental development, because if the agent starts seeing just massive errors all the time when you have an incremental development, the agent would just end up like just doing like a hack for fixing the thing. And at the end of the day, it's not like the development is not that you introduce a hole, it's that you start from 0 where everything is whole and you go completing. So I don't know if that.
Okay, maybe we can talk more offline about that. The other question is just my colleague Alp Kellis at UMD recently wrote a paper where he worked with database folks while they're building a database, and was doing a similar, had a similar thought, and he was doing manipulating the generator to try to avoid the places where things weren't done. Have you thought about that at all?
Yeah, but that would be like a different approach, but I guess generators are pretty complicated, like to avoid, to like try to manipulate the generator to avoid the holes where you could have multiple holes. I guess it's just, in my opinion, it's simpler to make the testing framework handle and take charge of the incompleteness.
Okay, thank you.
So it occurs to me that it might be useful to change some other things in your implementation as well. So for example, if you have a conjunction and the first conjunct is incomplete, but the second one fails, you might like to report that as an actual failure.
Yeah. That's the thing is, this is like a shallow reformulation. So this is not that precise. We don't enter the property that the user wrote. In the case of incremental certified programming, what they do is they enter the property and they actually take care of that case, and if you have ORs or implications and equivalences. So yeah, this is like an over-approximation, assuming you have like logical conjunctions, but that's actually.
So we have a couple questions online. So one is there was some confusion about just the negative test example that you showed in the talk. So they were curious if you could just maybe go back to that. Could you re-explain maybe what was going on with the negative test? So what was the main problem here and how did you fix it?
The thing was, in QCheck you have like this constructor for making tests. And I did, and I just, you can actually make like a negative test where you expect the thing to fail. So I wasn't just coding that. I completely forgot about that, and they are pretty useful because sometimes we actually want to find like race conditions, or we actually want to prove or check that something fails. So when I took care of that and I inverted it was just inverting the output of having that. But yeah, it's not, yeah.
So one more question online. Can you say, again, how to distinguish between incomplete fail with and unexpected case fail with in the implementation?
Oh, so what the implementation does is that we go recollecting the cases, we go recollecting where the user writes the fail with to do. So we actually catches that and considers that as incomplete. If it fails with any other thing, it's just an error, like it passes as an error. So that might sound as fragile, I know, because we're catching like a string in the middle of the thing. But the thing is, this way we don't have to do anything if I, like, say, want to upstream these changes. Maybe a better way to do that would be like having a dedicated exception to this case, and that would be more robust. Yeah.
Time for more questions, if anybody has more for Pablo. Okay, good. Well, in that case, let's thank Pablo very much. So we can go ahead and get Byron to set up. Joint work with Ben Wakefield and John Reppy. This is called self-tagging numbers. Byron, you ready?
Yeah. All right. Can people hear me, Mike? Good. Thanks, Sam, for the introduction. This is joint work with my advisor, John Reppy, and our undergraduate research assistant, Ben Wakefield. And we're here to go back to the basics and talk about how we implement numbers. So ML has traditionally implemented, well, most ML implementations implement numbers this way, using a 63-bit integer and implement every single number as 2n, implement number n with 2n plus 1. And we do this primarily to distinguish integers from pointers during runtime. And to make this problem, we'll recapitulate why we're doing this in the first place, what are sort of the popular alternatives, and what we plan to do about it. So the problem is as follows. If you're in a polymorphic context, such as this polymorphic ID function here, and GC sometimes has to run, if you just put integer there as is, you have no idea if that is a pointer or not, because you can always write an integer using all 64 bits that looks exactly like a pointer. So GC will be confused this way. But tag integers exploits the property that all pointers are aligned in the architecture's native alignments. So on a 64-bit integers, the bottom 3 bits will be 0. So if we put a 1 in there for the integers, then we will not have any confusions with what this is. So when the low bit is 1, it is an integer. That means that we shift everything over by 1 and use the rest 63-bit to encode the integer. This is obviously not the only way that we can make integers uniform. Another really popular approach is to have everything boxed. So this is the uniformly boxed approach that is really popular in dynamically typed languages, as well as most scripting languages such as Python. And the downside of this is quite obvious from the picture, because now that you have to allocate 3 words for an integer, you can do a little bit better by allocate integers into its special regions that contains only integers by saving 1 word, but you are still paying for the indirection. And in finding out what is the origin of these approaches, I find it really amusing that this is how Lisp 1.5 from 1961 is implemented. And as you can see from the manual, it says that these problems, referring to the DC problems, are solved by putting forwards in reserved section of memory called forward space. And the GC will stop collecting when they get out of the heap. I just find a bit of the history kind of amusing. And obviously, we're in a statically typed language. So we can also, there's another approach that exploits the parametricity of type variables. So because even if we write this function, implicitly we're writing this function as follows, right? It takes a type parameter, alpha, we'll take A, and then we know that inside this body, X will have one type, and that is that tick A. So every time we call this polymorphic function, we can sort of write a piece of metadata onto the stack, and that way we can recover this precise type information for this one. And this is the intuitions behind a really old paper by Andrew Appel. It's called Runtime Tags Not Necessary, as well as a really old implementation by Benjamin Goldberg that actually implemented this in translating, I don't remember what the source language is, but translate that to C. And it works by a really simple principle that because I have to call this ID with a type parameter, so as I'm calling the ID function and initializing the stack, I put a special metadata called int over there, and the GC, when GC runs, it scans the stack from the bottom, the oldest one, all the way down, and tracking each type variables, and that way we can recover all these information. Obviously, there's a third one, which is probably the most extreme solution to this. Is the one that popularized probably by Milton. It's called the monomorphization. So instead of having one copy of this ID function, there's nothing stopping us to use many copies of the ID functions specialized to each type that it is applied during the program. But doing so requires you to have the whole program available to you at once. And also, this is incompatible with sort of fancier type features such as polymorphic recursions and higher kind of types, because you can get infinite number of types during runtime, or some version of that. So all in all, considering all of these popular approaches, we all settle down into tag integers because it really gives us a balanced approach, right? The integers can still be represented as an immediate value, just like the monomorphic code and the untagged codes by the other things. And also, this is really easy to implement. Like we don't have to pay any special attentions into whole program compilations, and we don't have to hack into the GC to sort of pass runtime information from the mutator to the GC along the way. But also, there are a bunch of undesirable artifacts to this, right? One is that it reduced integer range by 1, which is not that much, but that means that any function that interacts with the runtime system or the POSIX, or the OS level code has to do this little conversion that you have to do. And most implementations to implement this will offer an int64 type for you to interact with the real world. And obviously, the int64 type is always boxed because we don't have that spare bit to encode the type information. And we pay a small runtime cost for every numeric operation. And I took this from my advisor's compiler class that tells students how to implement these. And then you can see that it's non-trivial to implement, say, multiplication and division in this. This is translating from one machine instruction into many. And then we certainly pay a runtime cost, albeit probably small, for these. And because of these pros and cons, SML, standard ML of the New Jersey compiler, which is the context that we're working on right now, working in, has been using tag integers since the very beginning. You can find it from Dave McQueen's 1987's paper about this that described tag integers. Right, and very recently, Melanson and Frano and Feely proposed a new technique of implementing floating point numbers in Scheme that really got us rethinking about the whole ordeals of tag numbers. And their title is Float Self-Tagging. And the idea behind that paper is actually, I think, very, very simple but very enlightening, which is that normally when you look at a float, unlike integer, there's no obvious way to place a tag, use all 64-bit, right? So most implementations, and also because floats are typically underutilized in functional languages, floats are boxed. But they realized that the top 3 bits of the exponent part of the floating point number is basically never used, or never has any interesting values in it. Specifically, the top 3 bits are almost always 0, 1, 1. That includes 1.7 times 10 to the minus 77 all the way to 2. And 100 encodes 2 to 2.3 times 10 to the 77. So you can safely assume that most programs operating have numbers operating in this range. So that means that the top 3 bits are always 0, 1, 1 or 1, 0, 0. So what they do is that when they need to sort of normally box this number, they instead just rotate this by 4, such that those 3 bits ended up at the bottom part of the number. And if they do that, and they just assume that the floats are always tagged with 0, 1, 1 and 1, 0, 0, they don't have to do anything to box this number. I think this is extremely clever, but also it tells us basically a general principles that we can use to exploit these sort of properties, which is that basically all data types, it's almost never the case that they're equally likely to occur. Like all bit patterns are equally likely to occur, right? And this obviously is true for integers, and I'm pretty sure it's for other types too. And if this is true, we can apply a reversible bit transformation to the value so that the common values have the desired bit patterns. And we'll talk about what desired means in a bit. And obviously we need to have a slow path for the remaining unfortunate cases that we just have to box the value. So this is what we plan to do. So what we're currently doing, which is that we're going to implement this in the standard of the New Jersey compiler. And we realize that not only does this technique give us the benefit of sort of doing away with 63-bit integers, which is pretty difficult to explain to people outside of this community at all. And we try to make the standard native integers default, and that means that we don't have to have a special types for int64. That means that arithmetic can work on the native instructions instead of having to do with this bit untagging stuff when we do arithmetics. And we also realize that this is more effective in a statically typed language like ML. And it's for the following 2 reasons. I'll explain them in a bit. So the number 1 reason is that we do not need precise type information at runtime, unlike Scheme, where it has to do runtime type checking. We only need to do this for GC. So we have more tags that are available to us to encode this number. And the second one is that we only have to tag integers when they transition into a polymorphic context. Right? If they're monomorphic, we can keep it in its native representation. So talking about the first point is that in the statically typed language, it would not go wrong if the type checker is sound. So we actually don't need to check the types during runtime. We're doing this solely for GC. And the GC doesn't have to know what the precise type of a value is. It only has to distinguish between the following 3 cases. One is that if it's a pointer, which means that GC needs to trace that value into its, the objects that is pointed to by the pointer. Or in our case, we use a copying collector. That means that we want to use the 0, 1, 0. Well, we'll use 1. Doesn't have to be 0, 1, 0. Doesn't be a special object for the header. That means that when you're scanning the 2 space, there's some optimization we can do with this. But these are the 2 cases that we really care about. Everything else we can just safely ignore. And so that's what we do. So we put everything else as a raw number. That really gives us 3/4 of possible bit patterns that can end up there that we can use as a raw value without any sort of boxing and unboxing. So this is our scheme for self-tagging. So we take an integer, and we look at the top 3 bits, similar to the argument made by Melanson et al., that the top 3 bits are almost always 0, 0, 0 or 1, 1, 1. That means that there's either a very small-ish, it's actually quite big if you think about it, positive integers, or a small, or close to 0 negative integers. So we can safely assume that it's almost always 0, 0, 0, or 1, 1, 1. And we left rotate by 3, so that those 3 bits ended up at the bottom bits. And we temporarily made the problem worse, right? Because the pointers are 0, 0, 0, and we just make a really likely number. We make it very likely that this is 0, 0, 0, which is not good. So we actually apply a sort of a stencil, a mask to it. So we XOR a pattern that's just the pattern that we found to work in most cases is 1, 1, 0 to it. So we get these 2 cases out of it, and you can see that neither of which is 0, 0, 0 or 0, 1, 0. The problematic patterns that we need to do. So that's our scheme to convert a number from native numbers to a uniform number, which is that we do a left rotation by 3 and XOR it with number 6, and we check if this is a pointer, means that it ends with 0, 0, 0, or is a header, it means that it ends with 0, 1, 0. If so, we box. We're unfortunate, but otherwise, we just leave it as is. Right, and for unwrapping, which there's an operation we call wrap that converts it from the native operations to uniform representation, and the opposite is called unwrap, that converts the uniform representation back to the native, and it's actually easier, simpler to implement, because we know that this has to be an integer by the type system, right? That if we're using a number as an integer here, that must be this an integer. So we only have to test if this is a pointer or not. If this is the pointer, we load it, we fetch it from memory. If not, we provide the inverse of the bit twiddling that we did previously. We XOR, which is self-inverse, and then we right rotate to get it back to its original shape. Right, and we know that this is actually really, really cheap to implement on a modern machines, and that is the entirety of the assembly code that implements this routine, right? So we do a right rotation by 61 because ARM doesn't have left rotation, and we XOR the pattern to it, and we do this test 5, right? Because 5 is 0, 1, 0, 1, so that it will only fail if the thing is 0, 0, 0 or 0, 1, 0. Right, and everything else will have a 1 bit to it, and then if that's the case, we jump to the slow path, which is allocation. Otherwise, we continue. Right. So in the fast path, there are only 3 instructions that we need to do to convert something from the native representation to uniform representation. Similarly, for unwrap, it's really the similar story that we test if it's a pointer. That means that the bottom 3 bits are 0. If so, we fetch. If not, we do an XOR and then do a right rotate of 3. Right, and because we leave 3/4 of the available bit patterns to encode such an integer, we have a lot of, the range of integers that we do not have to do anything. It's quite big. I believe in the scheme case, they only can do 1/4 of the static, assuming uniform distribution, 1/4 of the floating point numbers will be encoded this way, but we can have 3/4 of integers that can be encoded this way because only 2 patterns are reserved. So, if you apply, apply the bit mask backwards, that means that only values from -2 to the 61st. I'm not going to try to pronounce all these numbers. All these numbers needs to be boxed, which my claim is that the numbers in this range is rarely used. The only case that in practice we never seen those numbers in any of our benchmark cases, because probably all of them is intended to work on 32-bit machines, and certainly we don't have this. The only case where this occurs is when we do some hash functions where we have to compute, a hash. We'll obviously use all the bits pretty uniformly. So that's maybe the only case where this is likely. Right. So this is our scheme, and we talked about this is more effective in a statically typed language like ML. Also because, we only have to tag integers when they transition into polymorphic context, right? The same as the Milton case, when we have a monomorphic code, we know statically whether something is a pointer or integer, right? Because we can just look at its types. But we only have to tag integers when they transition into polymorphic code. That means that we keep all the numeric operations monomorphic, so they all assume or expect uniform int when you pass it to, say, operation like plus. So operation plus will have native integers as its expected input. And internally, we actually give int two types. One is called int, one is called int_unif. And I'm going to abuse the notation here because unif is actually a type family, not a type constructor, but just bear with me here. We use int to represent the native ints and int_unif to represent the uniform ints. And we generate coercions and wrap and unwrap when we try to change from one representation to the other. Right. So this wrap and unwrap operations actually is a broad spectrum operator, right? It doesn't just work on int64. We keep every single other integer's representations native too. So we used to not have int8s at all in the language. So every single character, for example, occupies all 64 bits because we have uniform representation across the board. But in this case, we actually do implement machine level sort of int8 type. But every time we need to go to the uniform representation with zero extend or sign extend, it doesn't matter because we're gonna, if it goes back, we'll truncate it back to its original size. And we also have a type in the IR called enum that is the constructor tag that is used for nullary constructors or constructors that you have to distinguish things. And we use the original tag implementation for those. So changing from one to the other is identity. And you can extend this tables downwards with other types using similar schemes. Right, and the scenario of New Jersey compiler already has machinery to generate representation coercions, especially it's internally, this was originally developed to use to unbox parameters when you go into functions such as unboxing tuples and so on. And it has a really standard system f omega IR. The only thing that is important in this is that we actually have explicit type applications and explicit type abstractions, the capital lambdas. Right, and we define a function called coerce that try to coerce between two types. If they're the same, it's identity. If it is tau to tau unif, we generate the wrap function. We call the wrap function for the specific type. And we do unwrap if we try to go the other way. And we lift this operator through the other type forms of type schemes, such as if we have a type abstraction with for all type, we basically eta expand it and coerce the middle. We have a tuple, we coerce each part. And if we have functions, this is important in a later slides, that we coerce the arguments into the expected type, and we coerce the arguments, the return values out of the function's native types. Right, so during lowering, we take this IR, we generate coercion terms at type applications. So we go through the entire of the IR, and we look at every single place where we have this type application form E applied to a type. And we make sure that we coerce that type into a uniform type. And that's the entirety of the transformation. It's just this, and all the other rules, such as walking down the tree, doing this thing at the edges. And what this means, again, as an example, what this means as an invariant, I guess, is that at runtime, all variables with polymorphic types are bound to values in their uniform representation, right? Because all type applications are applied to something of the type unif, right? We do not have any other types of type applications other than the one applied to a unif. That means that all variables, if they're instantiated as a polymorphic type, will have the type unif. So as an example, let's convert this ID function, which is applied to an int, using this rule. We'll realize that this is indeed applied to a type constructor, int here. And we generate this coercion term, and then convert the the end result expression to be E prime, which is converting the parameter to a mu unif. And this is the one that we have. So we try to coerce, well, obviously this now has a type int to int, and we try to coerce this type into an int unif to int unif. And following the rules, we just get wrap and unwrap going in and out of that function. So this is generated through the entire IR, and then we make consistent that these wrap and unwraps are always present. Sometimes this may be a no-op and an identity function, but for integers, we are actually using this to coerce things in and out of the uniform representation. Right, so obviously, to make this fast, the upstream optimizer will try to eliminate type applications as much as possible. So every time we have a type application, we have this wrap and unwrap or coerce terms generated for it. The upstream will try to inline these type applications as much as possible to basically do a local level type monomorphization or specialization. And we also have a pass called the specialization, type of specialization, and this is implementing a method presented by Bjorner in 1995's ML workshop. It's called the minimal typing derivations, which is trying to get rid of spurious polymorphisms. So say I have an ID function that is only used locally, and I realize that the ID is only applied to int. ID does not have to have a polymorphic type. ID can be typed as int to int. So we go through the entire tree, sort of bottom up, walk the tree bottom up, and we collect every places where local variables used and try to give it a specialized type. And the crucial invariance that we have is that the arguments of type applications are always something of unif. That means that garbage collector, when they try to see the values, will not see a raw representation anywhere. Right, and obviously coercions are generated. So in practice, what this means is that instead of having the arithmetics doing the tagging and untagging, we have the type system doing coercions when you're going in and out of the polymorphic boundary. So for the same code, sometimes you may have some arithmetics that you may want to do that performs a plus with a tag and untagging, a multiplication with tag and untagging, so on and so forth. But now, because everything is assumed to work on the native representation, it gets unwrapped rather, when it goes out of the polymorphic context into the monomorphic context and wrap it at the end of it. And notice that these doesn't have to be consecutive in code. This just has to be a sort of a continuous function calls that are all monomorphic, right? There's no polymorphic code in the middle. So it's not trivial for the backend, say LLVM, to pick up these patterns to optimize them. Right, so this is the central message, right? The self-tagging techniques that Melanson et al. Offers. It offers a cheap way to convert numeric values between uniform representation and their native representations. We have numeric permops, assume native representations from now on, standard, and compiler tries to keep representations native as much as it can, and we generate conversions when they enter and exit out of the polymorphic context. Right, so we implement this this is still ongoing. We implement this in the standard Melville, New Jersey compiler, and numbers are not great yet because the middle end, well, I guess the backend optimizer doesn't really optimize quite a lot of the common patterns out, so such as literal values of these wrapping and unwrapping are not really pre-calculated and lifted, which it really should, and it was doing that before. And closure conversions really doesn't like this new representation of integers for values that, for a reason that people may be able to find me afterwards and talk about it. Right. So, but we do see some positive news because if you see on the top of the charts, these are sorted by their sort of speed ups. I would say. On the top of it, we actually see quite a lot of speed ups by doing these optimizations because quite a lot of code that we write are sort of embarrassingly monomorphic, right? They do not actually need 63-bit integers everywhere and tagged. They are monomorphic. Not much wraps needs to be generated for these. And even so, the wrap implementation is quite cheap to implement. So we see a 30 or so percent speed up from using the tag representation for some examples. But obviously, you see the bottom of the chart that we have some really pathological cases where these are we're still investigating what's really happening. But hopefully we have faith and also that this will be a tractable implementation. All right, that's it. So I'm happy to take questions.
Okay, we have quite a few questions online, and so I'll try to kind of bounce back and forth, maybe between the room and online. We could start with a question over here. Yeah.
Thanks. Great. I'm a little worried that they're not that often these cases at the end. So I think this relates a lot to Xavier's work on boxing, unboxing.
That's true. Yes.
So in the worst case, you will box and unbox, right, instead of wrap and unwrap.
Yep.
And the problem with the coercions, and which is also why this is not used in OCaml, for instance, right?
Mm-hmm.
So that the box and unboxing, once you have polymorphic types like lists.
That's right.
Then when you are using these functions, then you'll unbox and unbox coercion.
That's right. Yeah. So in the compiler front end, we make this guarantee that every recursive types or arrays, for that matter, are incoercible. So we do not coerce any of these. We make sure that arguments going into a list are always in uniform representation already. So I guess that's sort of one way to get around with the problem. We would not go into and recursively coerce the entire list, for example. Yep.
So a question online, wondering about the common case for going in and out of the polymorphic context. So like probably the most typical case would be going in and out of generic data structures like lists and arrays. Is that right?
That's
and
right.
Are there other common cases that are kind of important to point out?
Well, common cases are if you have a generic table, for example, sometimes the keys will be if you generalize the keys to any sort of values, the keys will be actually in the wrapped representation. And as you said, the worst case that you do is just take a list of numbers and map and add one to it, right? Because every time you're doing a really kind of short operations followed by wrapping and unwrapping on either side. So tuples, that's right. Yeah, also tuples too. Yeah.
Question from the room, 1 second.
So one of the things you have to deal with is sort of rotating all the values to make the distinguished part at the bottom. But because I think if you're just dealing with 64-bit, you can sort of keep that at the top bits and sort of just perform a mask and say, if the top bit is 0, then it's a pointer. And if it's not all zeros, then maybe you could distinguish that. Or at the very least, do that for just the object header. Have you thought about that, or how much are what actually dominates the performance of the wrap and unwrap? Is the shifting matter at all?
Yeah, we probably need more data to answer that questions because doing instruction level performance profiling is quite difficult at this day and age because you have to consider branch predictions and speculative executions. So our hope is that it depends on what is the context around it. These bit level operations will be pipelined, and then basically you get them for free. And if we have a good enough branch predictor and to make sure that the slow path is not executed.
Just another question from online. Why is the tag 3 bits? And is it possible to get away with 2? Just a curiosity. And or is there some sort of experimental optimal size that we know about?
Well, the tag bit is 3 because we are 64-bit integer. We have 64-bit machines, and we know that the pointers always has 3 zeros at the end. It used to use 2 bits, obviously on 32-bit machines, because that's all you have for pointers. We use 3 bits just because if we have to reserve 2, it's better to reserve 2 out of 8 instead of 2 out of 4, right? So that's the reason why we use 3 bits as a tag bit. But that's solely because we're on 64-bit machines and pointers are 8 words align, 64-bit align.
Thank you. Just a comment and a question. It's not a good idea to mask the most significant bit because you have to build a huge constant that does not fit in an assembly instruction. So this is not the way to go. You really have to rotate. Then to get back to your solution, did you consider an option where you do not wrap and wrap, but you only wrap integers, and it's only at the numerical operation that you do the unwrapping? Because if indeed you are in the range of integers that are not allocated, then the branch predictor should be able to do a good job for you, and you will avoid the wrapping and wrapping that you have. Did you consider that?
Yeah, we sort of, well, this is generated at the sort of the very upstream of the compiler. The downstream compiler, if you see that, well, this is our things that we try to, I guess we will try to do is to fuse these operations together, right? You know, a wrap and a sort of integer plus can probably work together. Is that, is that what at all you were asking?
Not exactly.
Yeah.
You present wrapping and unwrapping. Why don't you keep integers always wrapped? And it's only at the operation level that you check, or that you do the unwrapping.
Right.
Maybe we can take that offline. I have another remark. There is something that I do not buy, is that normally you should not tag 000 for the object, but for the integers, and you tag object 001, and all the cost of the extra operation you mentioned just go away.
Yeah, I think we had this conversation offline with my advisor, and I think the argument is that not all architecture has the word sort of byte level integer offsets. Address offsets. Some architecture only supports address offsets at the with the pointer width. So you cannot subtract 1; you have to always subtract 8 or
yeah. But
8.
when you have an object, when you access a property, you just add an increment.
Mm.
Okay.
Yeah, so I believe the reason that we use 1 tags rather than 0 tags, and I think OCaml also uses 1 tags, by the way, is because while you might think you could just like say put a -1 offset when you do a pointer dereference. The problem is that the hardware says, oh, I'm fetching a word, a 64-bit word, so I'm going to scale that offset by 8. So I'm actually going to do -8 as my offset, not -1. And so I'm not actually, to get that -1, I'm going to have to do a separate instruction to do the pointer arithmetic at the byte pointer level, and then convert it into a word pointer to do the fetch. And so that, I think that's the reason why that choice was made back in 1987.
We should probably go get lunch. So let's stop here and let's thank Byron one more time. Okay, welcome everybody. So I'm very happy to introduce Michael Fulmer. He's going to tell us about functional programming with serialized data and probably the Gibbon compiler somewhere in there. So go ahead, Michael. Yeah, take it away.
Okay, yeah. So I'm going to be talking about functional programming with serialized data. I'm going to go through some background and motivation first. I think I probably do have to motivate this. You might not be someone who would otherwise care about data serialization. I wasn't before I worked on this project. Right? I don't think I need to sell you on algebraic data types, right? As the ML workshop, you know why they're great. We build these inductively defined data types out of sums and products with recursion and everything. They're in ML and Haskell and other mainstream programming languages. And some example applications here I've put suggestively. These are things that the compiler I'm going to talk about is good at handling. Abstract syntax trees for compilers, analysis, sort of thing, document trees, and then even in domains that are less PL-ish, so KD trees, for example, space partitioning. Right, these are cases where we can describe the data algebraically. It turns into a kind of tree. There are the nice properties of it. Right? Now, if we're trying to optimize the performance of these programs, or at least if we're if you can do such a thing, imagine you're a C++ programmer, right? And you're trying to optimize the performance of some sort of program that's operating on tree-like data. One of the first things that you might do is think about how this tree-like data is represented in memory, right? So there are tricks that you can do, right? You might be able to pack your tree into an array, for example. That's a common sort of HPC-ish kind of trick, right? Compress the representation, improve locality. These are things that would be nice to do, right? And if you are working in one of these low-level, potentially unsafe languages, these are tricks that are available to you. Right? Now, of course, we're working in our high-level type-safe languages like ML or Haskell, and these kinds of optimizations aren't exactly available to us because the runtime system tells us how the object is going to be represented in memory. This is part of the contract. We get a very nice high-level interface. Compiler and runtime system take care of that stuff for us. So another thing relating to the representation of data is that sometimes we need to send our data over a network or write it to disk. Right? So if you've heard this phrase going around, zero-copy serialization, right? So usually you would have a different representation in memory and on disk for your data, right? In memory, it's whatever the object format that your garbage collector likes. You have sort of headers, information, everything. Objects are connected by pointers. So it's a sparse representation. And if you want to send it over the network, write it to disk, you would have to serialize it into a dense, contiguous representation. Right? Well, with a zero-copy serialization framework, so like CAP and Proto, you can unify these two representations. Right? You can actually have the program operate directly on the same form of the data that you would send over the network. So then we no longer need explicit sort of serializing and deserializing. Right? You can just mmap the data, basically. So these are two motivations, right? Tweaking the performance of our tree traversals and getting rid of this marshalling cost. These are two motivations for why we might care about how our data is represented in our program. Right, so I'm going to be talking about the Gibbon project broadly. We just calculated this recently. It's been 10 years, and I was amazed to find that out. Right, so I started this project with my supervisor, Ryan Newton, 10 years ago. This is a programming language and a compiler that is designed for working at a high level in a type-safe way directly with serialized data in its serialized form. So the source syntax is a subset of Haskell or typed racket. But for this talk, I changed my code example syntax to be in ML. Hopefully it's appreciated. So this is involves ongoing research in both compiler optimizations and in semantics. We've had a lot of papers over the years, PLDI, ICFP, ECOOP, and including on Tuesday, we had this paper. The ordering is a little bit unfortunate because what I'm going to talk about now is great background for you to understand this. So they went in the opposite order. I'm not going to cover most of what's in this paper. This is sort of, think of this as like more advanced than what I'll be talking about. In fact, most of what I'm going to be talking about today is actually from this PLDI-19 paper. This is sort of one of the earlier papers that set up some of the main ideas. Right? And to do this, I have a running example I'm going to use. This is a running example that we use actually in a lot of our papers and talks. It's a slightly weird-looking binary tree. Right? So this is a binary tree that has nodes that are not labeled and leaves that are. Right? So here is an example. Tell me if I got the syntax right. And how I might construct something like this tree up here. Right? So nodes take 2 subtrees. Leaves take a single int. Right? So this is, like I said, a bit of a weird data type, but this is simple enough that we can do a lot with it. This is representative of sort of more complicated tree-like structures. Okay, so how would this be represented in memory? Right? Well, at a sort of coarse grain approximation, something like this. We need a tag to tell us whether something is a leaf or a node. If it's a node, it will need to have pointers, probably, to the 2 subtrees, which I've drawn here, capital N and capital L for the tags and a star for the pointer. Right? And if it's a leaf, then the tag is followed by the int. Right? Of course, I'm glossing over a lot of stuff here. We might have header information in these objects if that's required, and so on. This is sort of just generally how we might represent this. The point is that these are objects in the heap connected by pointers. Right? And in fact, we can write down roughly the C data type to represent this. Right? We have this enum that tells us if something is a leaf or a node. And then if it's a leaf, we have an int element. And if it's a node, we have 2 pointers to the subtrees. All right, so if I want to do something like walk through my weird binary tree and increment all the leaves by 1, right? I could do this with a recursive function. So in the leaf case, that's easy. I pattern match on a leaf, and I return a new leaf with the payload of x plus 1. And if it is a node, I pattern match, pull out the 2 subtrees, n1 and n2, and then recursively apply add 1 to n1 and n2 and build a new node. Right? So on this example binary tree, I would get something like this. So 1, 2, 3, 4 becomes 2, 3, 4, 5. Right? So this is sort of basic undergrad functional programming stuff, right? Now, I mentioned at the beginning that we're going to be talking about serialization. One way that I could serialize this tree would be a pre-order serialization. So this is the same data, right? But now we have the entire subtrees living in line in this array or byte string, right? So the n here tells us that we're a node. And immediately following that is the beginning of the left subtree, which again tells us we're a node. And immediately following that is an L telling us that we're a leaf, and then a 1. So that's this path here, starting from the node, the n, taking the first subtree down here, then taking the first subtree down here. All right, so we've compressed the data on top down to this representation below. All right, so we have no more pointers. Right? The tags and the whole subtrees are written in line. All right, now I want to apply add 1 to this serialized binary tree. So that's pretty great, isn't it? I can just sort of loop left to right. I don't have to follow these pointers around. So locality makes the computer happy, right? All right, so if we fix a traversal order and we serialize our data, what do we get? We get no more pointer chasing. We get good cache locality. We can avoid marshalling. I'm not going to talk a whole lot about this avoiding marshalling part. That's you can see more in the papers. But obviously, there are a bunch of catches here, right? I've made this look easy. What is the problem here, right? The data type at the top has some structure, right? Even the C data type has some structure, right? What about the data type down here? This, as far as the compiler is concerned, we get no help. That's just a bunch of bytes. So we're on our own. All right. So everyone, of course, here loves C++, right? What does this code do? It's not a rhetorical question. Can someone answer? Is this hard to read? So imagine this was a traversal of a much more complicated data type. It'd be harder to read, right? So do we have an answer what this code does? Yeah? Yeah. It is suggestively named add1. Yeah, yeah. So yes, this is in fact doing that add1. I would say as far as tricky C++ goes, this is not that bad. It fits in a slide. So what is it doing? It's taking in this in and out buffer. It's going to look at the beginning of the in buffer, see if it's a leaf or a node, right? If it's a leaf, it's going to write a leaf tag to the output buffer. It's going to increment the in and out buffer pointers. It's going to write the incremented value 1 by 1. And then it is going to skip past the size of an int in both of these buffers. So we started with this beautiful structurally recursive pattern matching program, right? And we've ended up with this. So, yeah, that's a typo in the comment. Yeah, sorry. So actually that leads into my next slide. So now what does it do? Yeah, I'm not incrementing the two buffers anymore. So this compiles, right? It does something. Right. So not only is this hard to read and write, this is extremely unsafe, right? Because the types here, byte star, that doesn't give us any protection of the invariance of this data type. So if I write my C++ code badly, I just corrupt this whole thing. Right. So I've hopefully motivated that it might be worthwhile to do this in a world where you didn't have to write the C++ code. So that leads on to, what is the goal here? Compile a high-level functional program down to an efficient low-level serialized traversal like we just saw, right, in a way that is type safe. Okay, so that leads to the given compiler, right? So the compiler roughly has these 3 phases. We have our source language, which we call highcal, our typed intermediate language called locale, and then a low-level IR called nocal. These names, I think we thought were clever more than a decade ago, and now we're stuck with them. All right, so I'm actually going to spend most of the time talking about the middle part. I'm going to start here and then branch out in the 2 different directions. And there's a reason why I'm going to do that. So the source language is actually not very interesting to look at from our perspective because it's essentially just a subset of Haskell. The interesting stuff is how do we get programs of that form down to the serialized representation, right? And this middle IR actually makes all of the details of the data representation and the enforcing of the invariance, it makes them explicit. Right? And from the point of view of like a PL perspective for PL researchers, this middle point, this is where we've done most of the interesting meta theory. Right? So we have a type system and a proof of type safety for programs that read and write the serialized data. Right? And these programs contain syntactic annotations and constraints that are used to enforce the invariance of the serialized data. Right? So this middle part, locale, right? So this is essentially a type-safe functional programming language with recursion and pattern matching, as you might expect. The things that set it apart is that constructors and types are annotated with a symbolic location, right? And these symbolic locations are the handle that we have to enforce that this sort of serializing of data in memory is done correctly, right? And so what we want is that if we know X has this type, for example, list.loc, then if we were to go into memory, right, into the heap at what this symbolic location loc represents, there would be a valid series of bytes that correspond to the serialization that is induced by the list data type. Does that make sense? Okay, so these locations are introduced, they're lexically scoped, they're introduced with this letloc form, right? So this binds one of these locations, right? And the type system enforces that each of these locations is written to exactly once, right? So at least with respect to writing, they're linear. We can read from them as many times as we want. Locations also live in regions, right? So we use the traditional let region binding form to bind regions, right? But our regions are a little bit different in that each region is one serialized data structure. Okay, so there are a couple of things that we can do with these symbolic locations, right? If you think of them essentially like pointers, we can do a kind of pointer arithmetic, but the type system prevents us from doing dangerous things, basically. There's a very limited set of these pointer arithmetic-like operations that we're allowed to do, right? So when we're introducing one of these symbolic locations, we can declare that it might be at the start of a region, for example. We can declare that it is plus some constant after another location, as long as that constant lines up with the size of a sort of fixed thing that we're going to write there, fixed size thing. But of course, not all of our data has a fixed statically known size if it's built by recursion. So if something is built by recursion, we can say that a location is after that. Or after says, however big this thing is at A, B is after that. Right, so these are the only ways that we're allowed to relate locations to each other. Right, and like I said, we need after because the size of recursively built values are not known statically. So we're going to get to that. This is the answer is essentially yes, but it's also calculated while the program is running, sort of implicitly. Okay, so I'm going to go through a simple sort of program fragment here. I'm going to show you at each step how the state of memory changes. This should build some intuition for why these things work the way that they do, right? So at the beginning, we make an empty region. Then we're going to reserve some space here, right? I've named this C. I don't know if you can see the letter there. Okay, so far in scope, I have a region R, and I have a location C, and there's nothing in that location. I'm going to reserve a location A that's sort of after the one at C, so now I have 2 blank cells in my region. Now I'm going to write a leaf to A that contains the payload 1, right? So that ends up being 2 cells in size. I want to bind B to be after A, right? So now I have an empty cell here and still have the empty cell at C. Right? Now that I have this location B in scope, I can write my second subtree there. So I have L1 and L2. And then finally, when I write the node down here, the only thing that this does operationally is drop that N right in place, right? So this might give you an intuition for example, why we had to reserve this space at the beginning, right? Because we needed to write this tag N to it. Any questions about this? So if I take these 3 times that I wrote data, I can check my types. So for each of these, if I look at the state of memory, right? So for the first one, at location L, there's an L and then a 1. At location A, rather, there's an L and a 1. That is, in fact, a valid serialized binary tree. So our invariant checks there. Same thing here. At that location, there is, in fact, a valid binary tree. And finally, down here at C, there is. Right, and if we'd gone wrong, right, if we built this incorrectly, it would have been possible to violate that, right? So if the type system wasn't working correctly, it would let us build something like the top here. And this would be bad, right? There is not, in fact, a valid binary tree, right? Because it has an N followed by an L and then a 1, and the rest of the tree isn't written. Right. So the type system prevents that and forces us to make sure that if we have something like this in scope and types, then when we look in memory, it actually is serialized in the way that we said it should be. Yeah? What would stop us from doing node YX? That's a great question. Yeah, so let's go back to our, I don't know if there's a faster way to make Keynote do this. Right, yeah, so the question was, what happens if down here I tried to do YX instead, right? Then in fact, the data would not be in the right place, right? So the type system, I'll get to this in more detail in a minute, but the type system symbolically tracks these constraints, right? So it would only type check if it can say that the location of this x is immediately following the c, and the location of this y is after the location of the x, if that makes sense. Yeah? Yeah. But it's essentially equivalent. I think this was a convenience for the sort of doing the semantics to have these be separate things, but yeah. Yeah, okay. Any more questions before I go on? Oh, I gotta go faster. Okay, so I'm probably not gonna go into too much detail of the type system because we don't have that much time, but we have way too many typing environments in our judgment, right? So like I said, we keep track of these constraints. I think some of the text got cut off there, but these are constraints on locations, right? And they're tracked symbolically in the type system. Right. So the operational semantics, we have a map from symbolic locations to essentially real pointers, pairs of region and index, right? And then the actual store that maps regions to heaps, which are arrays of cells. And then there's a well-formedness criteria that basically says all these typing environments that keep track of all this symbolic information, the constraints and everything, these agree with the state of memory. Right? And one of the key hammers that we have for enforcing this and improving type safety is what we call this end-witness relation. This basically says, given a actual starting point, like a region and an index, so a real pointer, right, and a type, so basically a raw pointer and a type of what's supposed to be there, right? We should be able to unfold the type and essentially do structural recursion and walk all the way through the data type and get to the end, right? And if we can do that, then this RI2, this following pointer, this is the pointer to the end of whatever it was pointing at, right? So we should be able to walk all the way through it and get to the end, right? So this is what we mean by witnessing the end witness. So using this rule, the starting address of the second field is obtained from the end witness of the first, and so on. They're chained all together to go through all the fields. And we have a invariant in the type system that if we have a location in scope, then it has an end witness, right? So this is the thing that would be violated if we were ever building an incorrect or invalid serialized value. Okay, so with all that together, we can finally write our safe add1 in this middle language. Right? If you look up here, this is still a tree, arrow tree, but now we have these annotations. There's some location A and B. If we look at the leaf case, this is still basically the same leaf case. The only difference is we've annotated the constructor with that we're putting the output leaf inside B. And this big node case, this is essentially that program we just went through. But instead of having literal leaves, here we have the recursive applications of that one. Does that make sense? Okay, so you might have some concerns, right? In fact, there are valid concerns at this point, right? So first of all, how can the compiler figure out where to put these location bindings, right? And what the location's annotation should be, right? I've said these are in the middle, right? And that the source language doesn't have them. So how can the compiler figure that out? And that leads to another more serious concern. What do we do about functions that don't fit this pattern, right? There are functions that are not necessarily going to be easy to figure out how to adapt them to this, right? So here's an example, right? If you use a singly linked list like this in your functional program, you probably are expecting certain asymptotic behavior when you cons something onto your list. You're expecting cons to be O of 1. But if I have this invariant of these data types being fully serialized, then consing something onto a list requires a deep copy of the entire list, which might be okay, might not be okay. The way that we handle this in Gibbon is we actually do allow pointers, but pointers are this optional extra thing, right? There's a new variant that we add to all these data types that says, okay, you can actually put a pointer to the same data type here. Right, so this actually brings up the sort of gradient of all the way between fully serialized and fully pointer-based. Right, so if you need to recover sharing, right, then consing 3 onto this would look something like this. All right, and Well, if our source program has sharing in it, then we have some choices here, right? So if our source program is something like let x equal whatever in node xx, right? That's what we're supposed to compile. Here we can either add an indirection, right, which is the default of what Gibbon does, or if what you want is you want no pointers, you want it to be just fully serialized, we put in a deep copy, synthesize a copy for the data type. Any questions about that? Make sense? And there are some trade-offs here, right? Okay, so another thing, another concern here. So this sum function, right? We say that this sum always traverses its input. So why is that? Well, when I match on the node, right, I bind x and y in the pattern match, and then I fully traverse x by summing that, and then I fully traverse y. Right? This is just like our add one, but not all functions are like this. Right? So what about this function rightmost? So rightmost matches on x and y, throws x away, and just recurs on y. Now, if you imagine the picture here, where this binary tree is fully serialized, what do we know? We know that there is a node tag, and then immediately following that is all of x. Right? So how do we get to y? Well, we have a couple of solutions here. One, and you can read the papers for more on this, we can change the data type of tree to store a sort of offset or a jump ahead pointer. So that after this node tag before the subtree, there's a pointer that allows us to jump over the x and get to the y. Right? So this is a trade-off. We're using a little bit more space, right, because we have to store that extra offset, but it allows us to write this function. And if we don't have that, we don't have the offset, what do we need to do? We need to synthesize a traversal of x, right? Because we have to walk through the entire thing to witness the end of it in order to find the beginning of y. Okay, so how does the compiler do this? So we have this thing that we call traversal effect inference, right? So functions in the source program may be incomplete traversals, right? They're perfectly valid functions, but they don't really fit this pattern that we need. So the compiler performs this inference to determine which of the input locations, so locations that have already been fully written to, which of them are fully traversed, right? And of course, what happens if there's no end witness, if an input location isn't fully traversed, then these are our options, right? Either we can make use of an indirection node, or the jump ahead node rather, or the compiler has to insert the dummy traversal. Right, so these are sort of edge cases that are required to make this work with arbitrary functional programs. Yeah. So the end witness was this relation I showed earlier where you look at a pointer in a type, and you should be able to sort of walk all the way through it and get to the end according to the type. So looks like I'm about out of time. I'm going to rush through the last few slides. All right, okay, so putting this all together, how do we get from high cal to low cal? We do what we call location inference. This is basically, it's sort of like region inference. We build these sets of constraints about where locations should be. And if we ever try to unify two locations that have already been fixed, then that's a sign that we need some sort of indirection, right? That we've violated the serialization assumptions. All right, so once we lower it, we get to something that looks more explicitly like pointer arithmetic. We call this cursor passing code. So this, if you look at it, squint at it, it looks almost like that C++ code we had earlier, right? We have this in and out buffer, and we explicitly manipulate it. And for rightmost, it's the same thing, except we're doing this additional read cursor to read this jump. Okay, I have a lot more benchmarks in the papers and everything, but just picking one out to show you. This is a tree walking benchmark. It's log scale, lower is better. Given right here is the orange one. Closest other one is Milton. And then in increasing levels of slowness, it keeps going up. Right, so see our papers for more benchmarks. I have some subsequent research to go through real quick. So we added parallelism in our ICFP 2021 paper. We compared against OCaml, PHP, and the excellent Maple compiler. We have optimizing data layout. So this reorganizes the recursive data structures in memory based on traversal orders using an ILP solver. We added garbage collection. right? And a copy and garbage collection can actually re-serialize data that has had indirections added to it. We have the ICFP paper from Tuesday that hopefully you all saw that adds this content addressable pointers and everything, and these explicit boundary types that mediate between sharing and serialization. We have in-progress work on what we call data type factoring. This is basically doing like an array of struct to a struct.array transformation for algebraic data types, which can lead to, for example, map over a list being vectorized. And we've pulled all this out, this is the work of my PhD student, into a standalone Haskell library. So it doesn't need a bespoke compiler, it is a shallowly embedded DSL in Haskell. Okay, so the conclusion here, I've talked about unifying this on-memory, in-memory and on-disk representation. And a general takeaway, even if you don't care about serialized data or anything like that, just think more about your data representation. All right, thank you.
Questions for Michael?
So great. You mentioned this thing with the pre-order. Is that a kind of a thing that is built in, or can you choose other?
Yeah, okay, that's an excellent question. Yeah, so everything I showed in this had a pre-order or serialization. We've speculated that there's no reason why that has to be. You can pick a different one, and we're investigating something a little bit more general, like some sort of function that maps the logical data to a serialization strategy. But right now, it is hard-coded in the compiler. It is pre-order serialization.
Other questions for Michael?
Maybe it's a weird question, but in one example, you had a type taking a tree, returning a tree, and then we have two different locations. It felt like then in the function, it seems redundant to then reference the location.
Yeah, so there is a lot of redundant information in this IR, yeah. In fact, you could even say that these location binding sites are sort of redundant, like there is only one correct thing to write there. What we're doing is sort of making syntactically explicit these invariants. Yeah, so the compiler sort of generates them so we can read them.
Cool. Thank you.
Yeah.
We should probably stop so we can get to the next talk. So let's thank Michael one more time. So setting up is Harry Goldstein. He's going to and just wait one moment, we get the live stream. Yeah, it's good. Great, okay. Harry, take it away.
Hi, everyone. My name's Harry Goldstein. I'm an assistant professor at the University at Buffalo. And today I will be telling you what I think it takes to support property-based testing in a programming language. So I'm going to answer the question, what does a programming language need to support property-based testing? Now, if you've been at ICFP, you probably know what property-based testing is. However, I'll do my 2-second spiel, which is you have some logical property that you want your function to satisfy. You have a generator, which produces a lot of random inputs to that function. And if a lot of those inputs succeed, then you can be confident that your property is true of your function. And if you find failures, then that's a counterexample in either your property or in your program. So I want to start with a kind of glib answer to this question, which is actually that I think it requires almost nothing to support property-based testing in a programming language. And this is because property-based testing is pretty straightforward at the simplest level. You have a type for properties, so this is going to map some random input to a Boolean value, which is either true if the test succeeds or false if it fails. And then you need a generator. And here I'll represent it as a stateful function that takes some RNG seed and produces a random value alpha plus a new seed. And if you have these two types, and you have a property and a generator, then you can run the property for n different times for n different inputs, and you can check that for each of those the function succeeds. And if you wanted to, and some languages do, this can be your whole PBT framework. However, I wouldn't really recommend it, and I wouldn't be giving this talk if this was my whole conclusion. So instead, I'm going to edit the question that I started with a little bit, and instead of asking what does a programming language need to support property-based testing, I'm just going to ask what helps a programming language support really ergonomic property-based testing. And so that's what the rest of this talk is going to be about. I'm going to go through some language features that I think you as language implementers and maintainers might consider adding to or strengthening in your languages if you want to support some of the sort of newest and greatest property-based testing technology. I'll start by talking about abstracting over effects. I think this is probably the most important one. Then I'll talk about metaprogramming. Then I'll talk about live visual feedback. And at the end, I'll talk about one which I originally expected to be a kind of linchpin of this talk. And then I think it might not actually be, which is some way of passing implicit arguments to functions. I'll get right into it. So let's talk about abstraction over effects. So this is a generator that's going to produce random binary trees. And it's written using the very simple generator type, which I had a couple of slides ago. So what's going on here, the generator is going to sample a bit, which is going to say whether we're going to produce a leaf or a node. If it's true, we'll produce a leaf. Otherwise, we're going to make recursive calls on the left and right, and we'll produce a node by sampling. We'll sample a value for the integer, and we'll wrap that all up together in a node. But what I think you might notice about this code is that it's really kind of verbose, passing this seed around. This is not just annoying to write, but also error prone. You may find that if you accidentally pass the same seed to two parts of the program, you're going to end up with correlations in your data that you don't want. Even worse, if you want to use a different kind of random number generator, for example, this generator, which does the same thing, now uses a seed splitting random number generator, which QuickCheck uses. The splitting random number generator, instead of being stateful, it has this split function which takes a seed and can split it into two independent seeds. And you use that instead to kind of pass the seed throughout the program. But this is even more error prone if you're doing it by hand, because now you can just forget to split the seed, and all of a sudden, again, you end up with unnecessary correlations. So what you want is some way of abstracting this effect away and writing the generator where you only think about the actual generator. And so monad syntax is good for this. I'm using the let star syntax from OCaml. And with this syntax, you now don't have to worry about either of your ways of passing the seeds around. You can just write the code that you wanted, which actually tells how to produce this data type randomly. And all of the rest of it gets kind of swept under the rug. And so you can have the seed passing style by defining your return and bind this way. You can have the seed splitting by doing a slightly different definition. But the nice sort of effect abstraction goes beyond just being able to swap out the randomness. As your PBT library evolves, you may want to do things other than randomness entirely in your generator abstraction. So for example, this version of return and bind tracks the choices that are made in the generator while it generates. And by tracking those choices, you can do some really interesting things. For example, you might be able to use those choices for shrinking. Just as a recap, shrinking, you find a counterexample, and then you want to kind of shrink it down to the smallest thing that still triggers the bug that you found. And so in this case, maybe we shrunk this tree to this other one because it turns out the values in the tree don't matter, it's just the shape of the tree that matters. If you have a generator abstraction that tracks choices, you can do a thing that the hypothesis library in Python does, and shrink the choices instead of the data. So you can have your string of choices, which you tracked while generating. You shrink that string of choices, and then you play the new choices back through the generator to get a smaller value. This is how hypothesis does kind of shrinking of data without worrying about kind of data type specific shrinking. Now there's a paper at the Haskell workshop maybe earlier today that suggests this might not be the best way to do shrinking, but that's not my point. My point is that by abstracting the effects in your generator, you get to play around with what that effect is without affecting your user's code. If you want to know more about some of this choice tracking stuff, there's the hypothesis shrinking paper, and then a couple of papers that I wrote during my PhD on kind of tracking choices and shrinking as well. Okay, so my takeaway from this first part is that being able to compose effects, for example, via monad syntax, gives you an ergonomic and declarative syntax for generators that also lets you implement some fun other things by modifying the underlying effects, for example, getting things like shrinking for free. Okay, next I want to talk about metaprogramming, and I'm going to split this part of the talk into two pieces. The first piece is going to be on metaprogramming for better compilation. And the stuff in this portion of the talk is coming from a paper called Fail Faster, which is going to appear at OOPSLA in a couple of months. And this work was done by Thea Ritchie and Joe Cutler. I was just there to help. The idea behind this paper is an idea that has been noticed quite a number of times before, which is that when you take a monadic language from Haskell and plop it into another programming language, you end up with some problems. In particular, you end up with the problem that your binds, this program up here, desugars to a bunch of calls to gen.bind, and each of those calls allocates a closure. And you're allocating closures and closures and closures. And if you don't do something about that, you're going to waste a lot of time in a very tight loop allocating a bunch of closures instead of allocating the data that you're trying to actually generate. And this gets even worse for other parts of the generator language. For example, we have this union combinator, which you can use, in QuickCheck we call it one of, which lets you sample from one of a bunch of different generators. But if you're not careful, you might allocate this list on every pass through a tight loop. And allocating that list over and over is, again, really wasteful. So what we do in Fail Faster is we use metaprogramming to ensure that the compiler actually compiles some of these unnecessary allocations away. So instead of this picture, we have this picture. We do still desugar the bind syntax to the calls to bind, but then we ensure that metaprogram rewrites those binds to the seed passing syntax that we wanted before, and that avoids allocating a whole bunch of extra memory. And just to show you one chart from the paper, as you might expect, as the number of binds in the generator increases, our approach gets more and more effective at making that generator faster. Now I want to talk about a different way that metaprogramming is very helpful for PBT, and that's for code generation. It turns out once you put a ton of work into making your generator language really good, everyone decides they don't want to write generators anymore. And this is true especially of, for example, in OCaml, base QuickCheck provides this deriving QuickCheck macro, which derives a generator for an algebraic data type. In Haskell, we have generic random for this. And in a paper that I wrote, which is a study with Jane Street, where we interviewed developers about their experience with property-based testing, they all said that it was really useful to be able to do this. They really liked the fact that they could automatically derive a generator. And part of the reason for this is that developers find writing generators to be a kind of distraction from a distraction. If writing code is the goal and testing is a distraction from that, then writing generators is a distraction from the distraction. So it's really great to be able to just automate some of this tedium away. There is a bit of a problem, though, which is that if you have a property like this, the generator you derive might not be the one you want. For example, this property checks that a list is sorted And if the random list is sorted, then it checks that inserting a value into that list results in a sorted list. Unfortunately, this precondition, the is sorted, means that if you're not very careful how you do generation, a lot of the values you generate won't be useful, right? Most of the generators that you'll get, if you're naively sampling lists of integers, most of those lists won't be sorted. And so I'm going to talk about now two papers that address this kind of problem. One is by Leo Lampropoulos' student, Segev Elazar-Mittelman, who's been awesome. And then the other one is myself and Hila Peleg and Cassio Torkson and some other friends. And I will sort of put these two side by side and then talk about each of them. So the specimen tool, which is based on a tool in QuickChick, derives generators based on inductive relations. So if you have an inductive relation that defines the precondition of your property, this derive generator command is able to derive a generator that satisfies that inductive predicate by construction. And it's doing it via a technique that is pretty similar to what's going on with the deriving QuickCheck macro, except it's doing a whole bunch of stuff to track. It's doing quite a lot more under the hood to actually manage the precondition itself. The other side of this is if you have your predicate not as an inductive relation, but instead as just a function. And so the Palamedes tool, which I developed, does that. So we have the same predicate, but now expressed as a function. And we have this tactic in Lean, which can produce a generator based on that predicate. And since this is the one that I worked on more closely, I'll show you a little bit about how it works. I think it really drives home why the metaprogramming is really useful. So what we do is we have a theorem. This theorem says there exists a generator, which is the generator we want. In particular, its support, so the values it can generate, is exactly the value satisfying the predicate P, which is our precondition to the property. And if we prove this constructively, we should just be able to pluck the generator out and use it. So let me show you this in action. Here, we're going to try to produce a generator for 2 or 3. Not the most interesting one, but it'll illustrate the point. So if we want 2 or 3, how do we generate one thing or another? Well, we should try to make a random choice. So we can apply this synth pick operator, which produces the generator pick with 2 arguments and gives us 2 subgoals, one a generator for 2 and one a generator for 3. And then we can apply this pure rule, which gives us a generator for any constant, so in this case 2. And then on the other side, we can also apply the synth pure rule to get a generator for 3. And this gives us the generator we'd expect, which is just a random choice between 2 and 3. The really interesting thing is that this sequence of tactics is not what the user actually writes. What they write is generator search. We've used proof search in Lean via Lean's extensive metaprogramming system to find this proof automatically, which then finds the generator automatically. And if you want to know more about this, you can find it in the search for random constrained random generators paper. Now, I know that most people don't do their everyday work in a language like Rock or Lean that has the full power to do this. However, I do think a lot of these ideas could be applied beyond a dependently typed setting. And so what I would love to see is something like this, where you could tack some of these predicate constraints onto your generator derivers in languages that aren't dependently typed languages and still get some of the benefits of the techniques that we've implemented. So my second takeaway here is that metaprogramming lets us manage generator compilation and also automate generator creation to make PBT more powerful and more effective. Okay, now popping back up, I want to talk about the last thing, which is live visual feedback. In a property-based testing environment, the most likely thing that you'll get as output is on the command line. And that will show you something like this, which says 100 tests run. And in this paper on making sense of property-based testing effectiveness, we found that actually you can do a little bit better in terms of giving people an idea of what's going on during testing. So we built this tool called Tyche, which shows developers visual feedback about what's going on while they're testing. And we found that developers are statistically significantly better at telling good generators from bad generators when given visual output like charts and graphs versus when given just textual output in a command line. Now, I think you could argue with me that really this isn't a language thing at all. This is about the language ecosystem. And indeed, Tyche is a totally language-independent VS Code extension. However, what I want to show you now is an example of this tied more deeply into a programming language and the benefits you can get from that. So let me do that. Let's see. There we go. Okay, so this is a widget built into Lean that is able to show you the distribution of a generator live as you edit it. So I have this generator here, which is producing natural numbers between 5 and 12. And you can see the distribution. What's going on is during compilation, it's sampling the generator 1,000 times and then putting this widget into Lean's info view. But the cool thing is if I drop down this details panel here and I drag, the visualization updates live. And what's going on here is that under the hood, when I drag this widget, it's editing the code itself, which is causing Lean to recompile live, which is then feeding back into the system that produces the widget and giving me this live update. And language environments like Dr. Racket and Rock also have things that can do this. I'm not saying that Lean's the only thing that can, but I do think this is relatively unique in a language ecosystem, and I think there's a lot to be gained here. I think we're leaving a lot on the table by not having these kind of interactive components to our language ecosystems. So let's see if I can. How do I get back? How do I get back? Okay, no, not that. It's the one thing I didn't check. There, got it. I just have to zoom back. Okay. Takeaway 3. By building live visual feedback into the language ecosystem, we open the door to new user experiences that help developers do their jobs better. Okay, now I want to talk, if there's just a second, about implicit arguments. Because when I set up this presentation, and actually when I've talked to people about this, their guess for what I'm going to say is type classes. They think I'm going to say like a thing you need for PBT is type classes. And indeed, the arbitrary type class in QuickCheck is great. And very useful for managing a bunch of generator dependencies. However, I'm going to argue that actually type classes are not the most important thing for property-based testing. And this is in part because they can be a bit of a trap. See, there's more than one generator for a given data type. And often you want to think more carefully about which generator you want when producing a composite generator. So the fact that you can just use arbitrary is sometimes tricking you into using a worse generator than you could otherwise be using. That said, I do think passing implicit things is useful for PBT sometimes. In particular, when in base quick check, you often have to pass things like shrinkers and printers manually, and that's a bit of a shame. And in the study with Jane Street, folks did point out that they wish they had things like modular implicits for stuff like this. Okay, just to wrap up, if you want to do property-based testing in your language of choice, you probably can. You don't need to do anything to it. You can just implement a simple PBT library and go to town. But if you do want to tailor your language to PBT, I suggest these three features. And indeed, I suggest these three features for things other than property-based testing too. I think these are three of my favorite features in a programming language, and that more languages should have all three of them. Thank you, and I'd love to take questions.
Thanks for a very nice talk, Harry. I want to make a comment on the live visual feedback, which was very nice. So you showed us the example, and in the example you were making a choice of an integer in a certain range, and I expect that the graphs, the probability should be uniform.
Yeah.
So if you draw enough samples, you should get a straight line.
Yeah.
Now, of course, we didn't really get a straight line. We were seeing the result of 1,000 samples, but they looked near enough.
Yeah.
But were they? How good are we at asking, does it look near enough? Really, we should do some statistical reasoning at that point. I wonder whether your live visualization could help with that statistical reasoning so that you can see directly whether or not you're getting probabilities that are the ones that you're expecting.
Yeah, that's a great point. I think absolutely. I think the visualizations could help with statistical reasoning. I do think often for PBT we don't need that rigorous statistical reasoning because we're mostly trying to get distributions that kind of look about right and get us into the parts of the space we care about. But I definitely do think we could be tricked by a diagram that, you know, there's just not enough samples. And so doing some statistics to figure out do we have enough samples, I think is a great idea.
Questions?
Which time?
The second one, the Palamedes sorted list.
Yeah.
I didn't follow the theorem. Yes. Okay, so go ahead to the theorem. Yeah, that one.
Yeah.
And then I think we want to go back after this, but let me speak first.
Yeah.
This is a good property, but I'm not sure how it rules out the naive generator that makes all lists and then filters them. Like if that is a generator, I think it would.
So the paper has more on this. We by construction, the search can't find that backtracking generator. Like we just don't give it access to the combinators that would need to do that.
So is the generator no longer a function?
No, it is. It's a matter of the synthesis rules we provide. We don't provide kind of arbitrary proof search over the whole world. We give it proof search over a particular system of rules, and those rules are constrained to kind of by construction generators, except in a few cases, but there's a lot of details in the paper on that.
Cool, thank you.
Back to John. So there's another idea that you haven't mentioned in the context of sorted lists. My favorite way of generating a sorted list is to generate a random list and sort it.
Yes.
My favorite way of generating a binary search tree is to generate a random list of elements and insert them into an empty tree. What's your reaction to those?
Okay,
So
a few answers. First, you can't always do it. If you want to generate well-typed programs, for example, there aren't a neat set of combinators that can do that thing. The second thing is that that relies on more of the code base. So you require a sorting function to produce the sorted list. You require an insert function to produce the binary search tree. And if you want these generators to be verified, not just sort of correct by an informal argument, then you need to prove things about those pieces of code, which is sometimes harder than just kind of generating the proof by construction. Yep. Okay. Yes. Yes. We have ongoing work right now taking the generators that come from Specimen, that come from Palamedes, and making their distributions better. I agree with you that sometimes you get more easily a better distribution by these other methods. The latest in, there's some, I'm not going to go into it because it's kind of, it's work that we're in the middle of trying to publish, but it's trying to be able to support that sort of all of the above in terms of kind of unifying everything under one kind of nice ecosystem.
I think we should wrap up. We can thank Harry one more time. Okay. And that wraps up the Emma workshop for this year. So thank you all, and see you next time.